Look up at the night sky on a clear, dark evening, past the familiar sprinkle of stars that make up our own Milky Way. If you could peer even deeper, past the faint glow of neighboring galaxies, your eyes would eventually land on one of the most colossal structures in the entire observable universe, the Coma Cluster. A swirling metropolis of thousands of galaxies, all bound together by the unbreakable chains of gravity, so distant that the light we see today began its journey to us when dinosaurs still roamed the Earth. It's a place of almost incomprehensible scale, where entire galaxies are merely points of light, and the spaces between them are filled with a ghostly, multimillion-degree plasma. And at the very heart of this cosmic city, there lies a true leviathan, a galaxy so immense it defies easy understanding. This is NGC 4889, a supergiant elliptical galaxy that serves as the gravitational anchor for the entire cluster. But what if I told you that this distant giant is far more than just a collection of ancient stars? What if it's actually a cosmic treasure chest sealed for billions of years, holding within it a collection of the strangest, most bewildering objects we have ever begun to uncover? The sheer scale of NGC 4889 is enough to humble anyone. Think of our own galaxy, the Milky Way, a majestic spiral 100,000 light-years across. Now imagine something nearly 20 times more massive, a vast, diffuse sphere of ancient suns, home to 1 trillion stars or more. At its core, there once lurked one of the most fearsome objects in existence, a supermassive black hole of almost unimaginable power whose appetite shaped the galaxy around it. That era of violent feasting has passed, leaving behind a quiet giant. But the legacy of that tumultuous past is what makes this galaxy so extraordinarily special. It's not just the sheer number of stars that captivates astronomers. It's the peculiar, the anomalous, the downright bizarre relics and formations that were forged in the extreme environments of this galactic core. We are talking about objects that challenge our very definitions, things that shouldn't exist according to our current models, cosmic oddities that whisper secrets about the most fundamental laws of physics. This video is an invitation to open that treasure chest. We are going on a journey to the heart of the Coma Cluster to explore 50 of the strangest objects hidden within NGC 4889. We will encounter stellar corpses that behave in ways that defy logic, witness gravitational puzzles that bend space and time into knots, and investigate enigmatic signals that hint at phenomena we are only beginning to grasp. This is not just a catalogue of weird space rocks, it is a detective story, a deep dive into the cutting edge of astrophysics, where every strange object is a clue to a larger mystery about how galaxies live, die, and what they leave behind. So prepare to have your concept of reality stretched, because the wonders we are about to explore will change the way you see the cosmos forever. To truly appreciate the first and perhaps most fundamental strange object in this galaxy, we need to venture right into its core, to the gravitational heart of the beast itself. Despite the galaxy's current state of serene calm, its center is occupied by a sleeping titan. The supermassive black hole at the core of NGC 4889 is not just large, it exists on a scale that is almost mythological. Current estimates place its mass at a staggering 21 billion times that of our own Sun. Let that number sink in for a moment. Compare it to the supermassive black hole at the center of our own Milky Way, Sagittarius, a star, which is a respectable 4 million solar masses. The black hole in NGC 4889 is over 5,000 times more massive. If you were to place it in the center of our solar system, its event horizon, the point of no return, would extend far beyond the orbit of Pluto, swallowing our entire planetary system with an unimaginable amount of room to spare. This is where the mystery begins. An object of such immense gravitational power should be the brightest, most violent place in the galaxy. As matter spirals into a black hole, it doesn't just fall in quietly. It gets torn apart, superheated to millions of degrees, and creates an intensely luminous disk of material called an accretion disk. This process turns a feeding black hole into a brilliant beacon known as a quasar, visible across the universe. Yet, when we point our most powerful telescopes at the center of NGC 4889, we don't see that brilliant beacon. Instead, we find an eerie silence. This behemoth is dormant, a ghost of its former self. It's like discovering the fossilized skeleton of a dragon that once terrorized the land but now lies still, its fiery breath long since extinguished. So, what happened? The leading theory is one of cosmic gluttony. Astronomers believe that in the distant past, during the galaxy's formative years, this black hole was indeed a hyperactive quasar, feasting on a vast and plentiful supply of gas, dust, and even entire stars that ventured too close. This era of violent consumption would have been a spectacular, if terrifying, sight. But a black hole's appetite is not infinite when it comes to its local environment. It appears that this black hole has already devoured nearly all of the available material within its immediate gravitational reach. It has essentially cleaned its plate. The violent feasting frenzies that once powered a brilliant quasar have subsided, leaving the black hole in a state of quiescence. With little new matter falling in, there is no fuel to create the intense radiation that would mark it as active. This dormancy presents us with a profound cosmic lesson about the life cycles of galaxies. The most massive black holes may ultimately be the architects of their own silence. Their incredible outbursts of energy during their active phases can blow away surrounding gas and halt the formation of new stars, effectively starving themselves for the future. The quiet giant at the heart of NGC 4889 is a testament to a glorious, violent past that has now passed, a relic of an era when this galaxy was a far more tumultuous and energetic place. Its current slumber is not a sign of weakness, but rather a signature of its ultimate power, a power so great that it consumed its very reason for shining. This strange, silent anomaly sets the stage for everything else we will discover, because the aftermath of its ancient feeding frenzy is likely responsible for seeding the galaxy with the other bizarre objects we are about to explore. But the silence of that central black hole tells only part of the story of this galaxy's violent history. If you know how to look, the evidence of its past cannibalism is written across the heavens in faint, ghostly script. Surrounding the main, diffuse glow of NGC 4889 are ethereal structures that at first glance seem like cosmic mirages. These are the ghostly stellar streams, vast ribbons of stars stretching for hundreds of thousands of light years, weaving through the darkness like celestial rivers. They are not part of the galaxy's main body. Instead, they are the cosmic scars, the lingering evidence of a feast that happened over billions of years. Each stream represents the corpse of a smaller galaxy that ventured too close to the immense gravitational pull of this supergiant, only to be torn apart, its stars scattered into these long, lonely arcs. The process of galactic cannibalism is a slow and violent dance. When a smaller satellite galaxy gets caught in the gravitational field of a giant like NGC 4889, it doesn't just crash into it like a car wreck. The primary force at work is something called tidal stripping. Think of it as the difference between dipping a donut into a cup of milk and smashing it with a hammer. The gravity from the larger galaxy exerts a stronger pull on the near side of the smaller galaxy than on its far side. This difference in pull, the tidal force, relentlessly stretches the smaller galaxy. Over many orbits it is pulled apart, its stars stripped away one by one, leaving behind these long, thin streams that trace the orbital path of the devoured victim. It's a process that can take billions of years to complete, a drawn-out act of cosmic destruction happening in extreme slow motion. What makes these streams in NGC 4889 so strange, however, isn't just their existence, it's their incredible faintness and their sheer number. Detecting them is one of the most formidable challenges in modern astronomy. They are so dim that their collective light is often lost in the glare of the galaxy itself, requiring incredibly sensitive instruments and sophisticated computer processing to tease their signal from the background noise. The fact that we can see them at all around a galaxy so far away is a testament to how many times this cannibalism has occurred. NGC 4889 isn't just a giant, it's a glutton, having consumed dozens, perhaps even hundreds, of its smaller galactic neighbors over the eons. These streams are the fossil record of its growth, showing us that it didn't form in isolation, but built its immense size through a relentless campaign of mergers and acquisitions. This leads to one of the most profound mysteries these streams present. The shape, the length, and the very existence of these tidal streams are not governed solely by the gravity of the stars we can see. They are exquisitely sensitive probes of the galaxy's total gravitational field, which is dominated by its halo of dark matter. The strange distribution and motions of the stars within these streams are providing astronomers with crucial clues about the invisible dark matter scaffolding that holds the entire galaxy together. Some streams appear too long and thin, others show kinks or twists that are difficult to explain with simple models. These anomalies suggest that the dark matter halo of NGC 4889 might not be smooth and spherical as we often assume. Instead, it could be lumpy or even shaped more like a gigantic football, with its gravity sculpting the streams in ways we are only beginning to understand. These ghostly ribbons of stars, therefore, are not just remnants of past destruction. They are active experiments, cosmic tools that allow us to map the invisible and test the very foundations of our understanding of gravity and matter on the largest scales. And while the ghostly stellar streams tell the story of galaxies that were torn apart, our next strange object is a survivor, a galactic paradox that somehow endures in this hostile environment. Orbiting the immense NGC 4889 is an object so faint, so ethereal, that it pushes the limits of what we can even classify as a galaxy. Imagine a collection of stars that spans a volume similar to our own Milky Way, but contains so few stars that its total brightness is no greater than that of a single, dense globular cluster. This is an ultra-diffuse galaxy, a cosmic ghost ship adrift in the gravitational wake of a titan. If you were to fly through it, the space between its stars would be so vast and dark that you might not even realize you were inside a galaxy at all. It's a place of profound emptiness, a gauzy, faint smudge against the blackness of space that presents a colossal puzzle. How does something so fragile, so tenuous, possibly hold itself together against the overwhelming tidal forces of its colossal host? The very existence of this ultra-diffuse satellite galaxy defies our basic intuition about gravity and structure. Think of it like a wisp of cotton candy trying to survive intact next to a powerful industrial fan. The gravitational pull from NGC 4889 should, in theory, be more than enough to shred this delicate object, pulling its sparse stars away and adding them to the ghostly streams we just discussed. The fact that it hasn't been torn apart suggests there must be something we cannot see providing it with an invisible backbone, an internal strength that belies its faint appearance. This is where the mystery of dark matter comes roaring back to the forefront. The leading theory is that this galaxy is not actually diffuse in terms of its total mass. Instead, it's desperately lacking in the stars that make it visible. It could be absolutely filled with dark matter, creating a massive, powerful gravitational halo that binds its few visible stars together against the external pull. In this scenario, the galaxy is like a ghost with immense strength. Its visible form is faint, but its invisible presence is mighty, a gravitational fortress that allows it to weather the storm. However, there is a compelling alternative theory that adds another layer of intrigue. Perhaps this object wasn't always so diffuse. What if it was once a more typical, compact dwarf galaxy that had a recent, incredibly close encounter with NGC 4889? This brush with the giant wouldn't have destroyed it outright, but could have triggered a violent internal transformation. The tidal forces during this near miss might have violently stripped away a large amount of its gas and loosely bound stars, puffing up the remaining stars into the vast, diffuse cloud we see today. It's a cosmic trauma story where the galaxy survived the encounter but was left permanently scarred and stretched, its structure permanently altered by a gravitational shock. This would make it a temporary survivor, a galaxy in its final stages of being dismantled, offering us a rare snapshot of a slow-motion dissolution. Studying this object is like trying to understand the history of a ghost. Astronomers use its properties, the motions of its stars, its exact shape, and its distance from the giant, to run sophisticated computer simulations, trying to rewind the clock and see which story fits best. Is it a galaxy that was born strange, a dark matter-dominated relic from the early universe that never managed to form many stars? Or is it a more recent victim of galactic violence, a testament to the destructive power of its environment? Each possibility reveals something profound. If it's held together by dark matter, it challenges our models of how dark matter clusters in the universe. If it's a tidally disturbed object, it provides a unique laboratory for understanding the precise mechanisms of galactic disruption. This faint, seemingly insignificant smudge of light forces us to confront the complex and often violent interactions that shape the lives of galaxies, proving that even the quietest, most overlooked objects can hold the keys to the universe's deepest secrets. While the ultra-diffuse galaxy clings to existence on the outskirts, a different and far more dramatic fate awaited other stars that once orbited too close to the galaxy's sleeping heart. If you could rewind time by a few million years, you might witness one of the most spectacular events in the cosmos, the launch of a hypervelocity star. These are not merely fast-moving stars, they are stellar projectiles, cosmic bullets fired from the galactic center with such immense speed that they are flung out of the galaxy entirely, destined to wander the emptiness between galaxies forever. The discovery of these stars racing away from NGC 4889 provides us with direct, tangible evidence of the incredible forces that once raged at its core, a signature of the black hole's past violence written in the motion of these lone travelers. The likely mechanism behind this stellar catapult is a gravitational slingshot, a complex dance involving three bodies, the central supermassive black hole and a binary star system, a pair of stars happily orbiting each other. Imagine this binary pair drifting perilously close to the black hole's overwhelming gravity. The gravitational pull on the star that is closer to the black hole becomes vastly stronger than the pull on its companion. This difference violently rips the binary system apart. In a flash of cosmic energy, one of the stars is captured by the black hole, falling into a tight, doomed orbit. The other star, in a reaction that obeys the conservation of energy, is flung away at an astonishing speed, as if it were the stone released from a sling. This process, known as the Hill's mechanism, can accelerate a star to velocities exceeding 1,000 kilometers per second, far beyond the escape velocity needed to break free from the galaxy's gravitational grasp. The trajectory of these ejected stars is a one-way ticket into nothingness. Once they break free from the gravitational bonds of NGC 4889, they enter the truly intergalactic void. For millions, even billions of years, they will travel through the near-total emptiness of the intracluster space within the Coma Cluster, their light becoming a lonely beacon in an ocean of darkness. Unlike most stars that live and die within the nurturing environment of a galaxy, surrounded by gas clouds and neighbors, these hypervelocity stars are true orphans. They will never again encounter a molecular cloud to trigger new star formation, nor will they be part of a galactic disk. Their entire existence from the moment of ejection is a solitary journey, a testament to the fact that the universe can be both majestic and profoundly lonely. But these stellar exiles are more than just cosmic curiosities. They are invaluable tools for astronomers, By tracing their paths backward, scientists can literally map the gravitational field of the galaxy they fled from. The exact speed and direction of a hypervelocity star serve as a forensic record of the event that created it, offering clues about the mass and spin of the central black hole itself. Furthermore, as these stars travel across the galaxy and into the intergalactic medium, they act like probes, and their light can be analyzed to reveal the properties of the thinly spread gas and dust they pass through, material that is otherwise almost impossible to detect. Each one is a messenger carrying information not just about its origin, but about the environments it traverses on its endless journey. In their desperate flight, they illuminate the secrets of the darkness they are condemned to cross. From the high-speed escape of stellar exiles to the delicate dance of galactic cannibalism, every strange object we've encountered so far points toward the invisible hand of gravity, sculpting the visible universe. But to truly understand the sheer power required to hold a supergiant galaxy like NGC 4889 together, we must venture into the realm of the unseen. This brings us to our fifth strange object, which is not an object you can photograph in any conventional sense. It is the galaxy's vast, encompassing shroud of dark matter, the mysterious, invisible substance that makes up the overwhelming majority of its mass. And the strange part isn't that this halo exists, it's that its structure is deeply, perplexingly wrong. The dark matter halo of NGC 4889 behaves in a way that challenges the most fundamental computer simulations of how the universe works. Think of a dark matter halo as the galaxy's true skeletal structure. The stars and gas we see are merely the visible flesh draped over this invisible framework. For a galaxy to be stable, especially one as massive as this, its dark matter must be distributed in a particular way, creating a smooth, predictable gravitational gradient that keeps everything in orderly motion. Cosmological models based on decades of observation and theory predict that this halo should have a specific density profile. It should be densest at the very center and become progressively thinner and smoother as you move outward, like a cosmic fog that gently fades into the void. This is the standard model, the bedrock of our understanding of cosmic structure formation. Yet, when astronomers study the actual gravity of NGC 4889 using a technique called gravitational lensing, the results are startlingly different. Gravitational lensing is one of the most powerful tools we have for probing dark matter. It relies on a prediction from Einstein's theory of general relativity, that massive objects warp the fabric of space-time around them. When light from a distant background galaxy travels through the gravitational field of NGC 4889, its path is bent just like light bending through a lens. By meticulously measuring the subtle distortions in the shapes of thousands of these background galaxies, scientists can create a detailed map of the foreground galaxy's total mass distribution, revealing the shape and density of its dark matter halo. The map they get for this galactic titan is anything but smooth and predictable. Instead of a serene, symmetrical fog, the halo appears lumpy and asymmetrical. There are unexpected concentrations of mass and puzzling voids, as if the dark matter is clumped together in ways that our models say it shouldn't be. It's like expecting to find a perfectly round, dense ball of yarn, only to discover a tangled, irregular knot with thick patches and thin spots. This discrepancy is more than a minor anomaly. It strikes at the heart of our understanding of dark matter's fundamental properties. One compelling explanation is that this lumpiness is a fossil record of the galaxy's violent history of mergers. The standard simulations often model galaxy formation in relative isolation, but NGC 4889 is a product of relentless cannibalism. Each smaller galaxy it consumed would have brought its own small halo of dark matter into the mix. Perhaps these smaller halos haven't yet fully merged and smoothed out within the larger halo, leaving behind dense, surviving clumps or subhalos of dark matter. The galaxy's gravitational halo, therefore, wouldn't be a single, smooth entity, but a complex amalgamation of many smaller halos that are still in the process of dissolving, like streams of different colored ink not yet fully mixed in a glass of water. However, a more radical possibility is that this discrepancy is telling us something profound about the nature of dark matter itself. The most popular model assumes dark matter is cold and collisionless, meaning its particles move slowly relative to light and almost never interact with each other or with normal matter except through gravity. This model has been incredibly successful on the largest scales, but if dark matter had even a tiny ability to interact with itself, if its particles could collide and scatter, it would dramatically alter the structure of halos. Self-interacting dark matter would tend to smooth out the dense central cores of halos and could also prevent the formation of as many small subhalos, potentially explaining both the lumpiness we see and the surprising lack of certain small satellite galaxies around giants like NGC 4889. This strange, lumpy halo forces us to confront a critical question. Are we seeing the complex aftermath of a violent life, or are we glimpsing the first cracks in our theoretical foundation? The smooth halo predicted by simulations is a product of the simplest assumptions about dark matter. The messy, complex reality observed around NGC 4889 might be the universe's way of showing us that dark matter is more interesting and perhaps more complex than we ever imagined. Every anomalous clump and void in its gravitational map is a clue, a piece of a puzzle that could ultimately reveal the true identity of the universe's most dominant, yet most elusive component. Moving outwards from the galaxy's invisible dark matter halo, our attention is drawn to a spectacular and ancient celestial jewelry box encircling the giant. Orbiting far out in the galactic periphery is a strange and distinct ring of globular clusters. These are not your average star clusters. Globular clusters are dense, spherical swarms of up to 1 million stars each, bound together so tightly that their centers can appear as a single, blazing point of light. Most large galaxies, including our own Milky Way, have a retinue of these ancient objects scattered around them in a more or less random, cloud-like distribution. But the arrangement around NGC 4889 is anything but random. Here, a significant population of these clusters is organized into a vast, coherent ring, a shimmering halo of stellar antiquity that traces a circular path around the galaxy like a string of cosmic pearls. This ring-like structure is a massive clue, a fossilized imprint of a monumental event in the galaxy's deep past. The predominant theory among astronomers is that this ring is the direct result of a major merger, a head-on collision between NGC 4889 and another large galaxy billions of years ago. Imagine the cosmic violence of such an event, not a gentle grazing, but a colossal impact that would have sent shockwaves through both systems. During a merger of this scale, the galaxies don't simply crash and stick. They pass through each other, their stars mostly avoiding direct collisions due to the vast distances between them. However, their gravitational fields become entangled in an incredibly complex dance. It is this gravitational turmoil that can strip globular clusters from the smaller galaxy and fling them out into wide, looping orbits, eventually settling into a stable, rotating ring around the victorious larger galaxy. The ring we see today is the calm after the storm, the orderly final state of a process that was once pure chaos, a lasting monument to a forgotten galactic empire that was consumed. The stars within these clusters add another profound layer of mystery. They are among the oldest stars in the entire universe, having formed not long after the Big Bang itself. When we point our telescopes at these clusters, we are essentially looking back in time over 13 billion years. The light we capture today began its journey when the universe was in its infancy, a hot, dense, and rapidly expanding fireball. The chemical composition of these stars is a pristine record of that early era. They are what astronomers call metal-poor, meaning they contain very low concentrations of elements heavier than hydrogen and helium. This is because they formed before generations of stars had lived, died, and exploded in supernova to seed the cosmos with these heavier elements. Studying them is like analyzing a fossil that predates the existence of complex life on Earth. They offer a pure, unadulterated sample of the primordial gas from which the first structures condensed. This ancient stellar population presents a fascinating puzzle when we consider the ring they inhabit. How did these incredibly old clusters, which must have formed very early in the history of the universe, end up being organized into a structure that seems to be the result of a more recent merger? The answer lies in the timeline of cosmic evolution. A recent merger in astronomical terms could still have occurred 8 or 10 billion years ago, when the universe was about half its current age. The clusters themselves were already ancient by that point, having orbited their original host galaxy for billions of years. The merger event did not create the clusters, it simply rearranged them, organizing these pre-existing celestial relics into the dramatic ring we observe today. This means the ring is a kind of cosmic double feature. It tells the story of the very first stars through the cluster's internal chemistry, and it simultaneously tells the story of a dramatic, mid-life galactic collision through its large-scale geometry. The stability of this ring over billions of years makes it an exquisite natural laboratory for testing gravity on a grand scale. The precise positions and velocities of these clusters are governed by the combined gravity of all the mass within the galaxy, both the visible stars and the invisible dark matter halo we discussed earlier. Any slight deviations in the ring's shape or unexpected motions of the clusters within it could hint at the presence of those elusive dark matter subhalos or anomalies in the gravitational field. Furthermore, because these clusters are so old and their orbits so stable, they act as tracers for the galaxy's long-term evolution. They are like a flight data recorder for the galaxy, preserving a memory of the violent events that shaped it. By meticulously mapping this ancient ring, astronomers are not just admiring a beautiful structure, they are reading a chapter from the biography of a supergiant galaxy, a chapter written in the slow, precise motion of stellar swarms that have witnessed almost the entire history of the cosmos. Yet for all the grand, slow-motion drama of galactic mergers and dark matter halos, some of the most intense and violent events in NGC 4889 unfold on a much smaller, far more furious scale. Tucked away within the vast expanse of this giant galaxy is a celestial partnership that has become a beacon of high-energy fury, an X-ray binary system in the midst of a spectacular outburst. This is not a serene pairing of stars, it is a vampiric relationship between a stellar corpse and a living star, a dance of death that periodically lights up the galaxy in some of the most energetic radiation the universe can produce. To understand the sheer power of such a system, picture a binary pair locked in a tight, frantic orbit. One member is a dense stellar remnant, either a neutron star or a stellar mass black hole, the leftover core of a massive star that died in a supernova explosion. Its partner is a more typical, living star. They orbit so closely that the immense gravity of the dense remnant begins to strip material directly from the outer layers of its companion. This stolen gas doesn't fall straight in. Instead, it spirals down toward the remnant, forming a superheated, whirling disk of plasma known as an accretion disk. The friction within this disk heats the material to temperatures of millions of degrees, causing it to glow not in visible light, but in the far more energetic X-ray part of the spectrum. In its quiet state, such a system is merely a faint X-ray pinpoint, but during an outburst, the rate of accretion increases dramatically, and the system can become thousands of times brighter, outshining all other X-ray sources in the galaxy combined. What makes this particular binary system in NGC 4889 so strange and fascinating to astronomers is not the outburst itself, but its utterly unpredictable timing. In many similar systems found elsewhere in the universe, these outbursts follow a rough schedule, flaring up every few months or years in a cycle that astronomers can sometimes anticipate. The pattern is tied to the stability of the accretion disk. Once a critical density of material builds up, it triggers a runaway heating process that leads to the brilliant flash. But the system we're observing in this distant galaxy defies these expectations. Its outbursts occur erratically, with long periods of silence followed by sudden, intense flares that seem to have no apparent rhythm or reason. It's as if a geyser erupted with tremendous force, then went quiet for a decade, only to explode again the following week, completely confounding any attempt to predict its behavior. This strange irregularity is a goldmine of information, pointing to a highly unusual and dynamic environment. One leading theory suggests that the chaotic nature of this binary is a direct result of its location within the super-crowded core of NGC 4889. In such a dense stellar environment, the binary system is not orbiting in isolation. The gravitational pull from countless passing stars could be constantly perturbing its orbit, minutely altering the distance between the two stars. Even a tiny change in separation can have a dramatic effect on the rate at which material is siphoned from the donor star, essentially jiggling the pipe of the accretion flow and disrupting any stable pattern that might otherwise form. The binary is living in a cosmic mosh pit where it's constantly being jostled by its neighbors, preventing it from settling into a regular routine. Another compelling possibility is that the donor star itself is unusual. Perhaps it is a variable star, one that undergoes intrinsic changes in its size or luminosity. If the star periodically swells and contracts, the rate at which it donates material to its greedy companion would change accordingly, turning the accretion stream on and off like a faulty tap. This would make the outburst a reflection of the donor star's own life cycle, a cryptic signal of stellar pulses encoded in bursts of X-rays. Unraveling which of these scenarios is correct, or if it's a complex combination of both, requires painstaking observation. Each unpredictable flare is a clue, and by measuring the exact energy spectrum of the X-rays and how quickly the outburst rises and fades, astronomers can piece together the physics of this violent relationship. The significance of this erratic beacon extends far beyond the binary system itself. It serves as a natural laboratory for studying accretion physics under extreme conditions that we could never replicate on Earth. The process of how matter falls onto a black hole or neutron star is fundamental to understanding how these objects grow and how they influence their surroundings. Furthermore, because X-rays can travel through clouds of gas and dust that block visible light, these outbursts act as brilliant flares that illuminate the interstellar medium of the galaxy. As the X-rays travel toward us, they are subtly absorbed by atoms in the gas clouds within NGC 4889, allowing scientists to analyze the chemical composition and density of material that would otherwise remain invisible. This one strange, unpredictable object is therefore a powerful tool, its violent tantrums helping us map the hidden guts of a galaxy far, far away. While the X-ray binary flares with its unpredictable violence deep within the galaxy, our attention is pulled to a far more ethereal and mysterious structure on a truly colossal scale. Drifting through the immense void between galaxies in the Coma Cluster is a strange object that challenges our very notion of what constitutes a celestial body. A massive, isolated cloud of primordial hydrogen gas, so vast it could encompass entire galaxies, and it appears to be on a direct collision course with NGC 4889. This isn't a cloud within the galaxy, it's a solitary wanderer in the intergalactic darkness, a ghostly behemoth that emits no light of its own. The profound mystery is that this cloud seems to be entirely alone, a cosmic orphan with no visible galaxy to call home, leaving astronomers to puzzle over its incredible origin story. The existence of such a vast, isolated reservoir of gas presents two equally fascinating possibilities. The first is that we are looking at a genuine relic, a fossilized pocket of material that has remained virtually unchanged since the dawn of time. In the earliest moments of the universe, after the Big Bang but before the first stars and galaxies ignited, the cosmos was a hot, dense soup of fundamental particles. As it expanded and cooled, hydrogen and helium atoms formed in a process known as recombination. Most of this primordial gas eventually collapsed under gravity to form the first stars and the proto-galaxies that would grow into the structures we see today. But this cloud could be a rare survivor, a patch of that original material that, through a fluke of cosmic dynamics, never fell into a galaxy. It has been drifting in the profound emptiness for over 13 billion years, a pristine sample of the universe's raw building blocks, untouched by the stellar furnaces that have since enriched the rest of the cosmos with heavier elements. The second, and perhaps more dramatic, explanation is that this cloud is the ghost of a galaxy that no longer exists. We've already discussed how NGC 4889 cannibalizes its smaller neighbors, tearing them apart into stellar streams. But what if a victim was so small, so fragile, and composed almost entirely of gas that the tidal forces from the giant completely vaporized it? The process would have been incredibly effective. A small, gas-rich dwarf galaxy venturing too close would have its stars stripped away to form the faint streams we can detect. But its gas, being more diffuse and responsive to pressure, could have been completely shredded and dispersed into a vast, amorphous cloud. In this scenario, the hydrogen cloud is the final, dissolving breath of a galaxy that was utterly annihilated, its identity erased, leaving behind only this tenuous atmospheric shroud as its tombstone. What makes this object an invaluable scientific tool, however, is not just its mysterious past, but how it interacts with the light from more distant cosmic objects. Since the cloud itself is dark, we cannot see it directly. Instead, we detect its presence through the magic of absorption spectroscopy. When the intense light from an even more distant quasar, a brilliant beacon located far behind the Coma Cluster, travels through this cloud on its multi-billion-year journey to our telescopes, the gas leaves a unique fingerprint on the light. Specific wavelengths of light are absorbed by the hydrogen atoms in the cloud, creating dark lines in the quasar's otherwise smooth spectrum. It's akin to holding a stained glass window up to the sun. The specific colors that are missing tell you exactly what elements are in the glass. By analyzing these absorption lines with exquisite precision, astronomers can extract a wealth of information from this ghostly cloud. They can measure its exact chemical composition, confirming whether it is truly pristine primordial gas or if it contains traces of heavier elements that would betray a past history of star formation. They can determine its temperature and density, revealing the physical conditions within the intergalactic medium. Most remarkably, by looking at the precise shape and shift of these absorption lines, they can calculate the cloud's velocity, confirming that it is indeed moving at tremendous speed toward NGC 4889. This single dark fingerprint allows us to study an object we cannot see, to weigh it, to clock its speed, and to read its history, all from the light that passes through it. This falling cloud also represents a potential future feast for the sleeping giant. While the central black hole may be dormant now, the infall of such a massive amount of fresh, cold gas could, in the far future, reignite a period of dramatic activity. As the cloud plows into the outer halo of NGC 4889, it would experience shock waves compressing the gas and potentially triggering the formation of new stars in a faint outer ring. Some of this gas might eventually spiral all the way down to the galactic center, providing the fuel needed to wake the supermassive black hole from its slumber and transform the galaxy's core into a brilliant quasar once more. This silent, dark cloud, therefore, is not just a relic of the past, it is a herald of a possible future, a slow-moving catalyst for a transformation that will unfold over hundreds of millions of years, a reminder that even the quietest giants may not have reached the end of their story. Yet, amidst these external dramas of falling gas clouds and stellar exiles, the galaxy itself presents a grander, more subtle mystery in its very essence. If you were to take a broad, spectrum-measuring look at the light emanating from NGC 4889, you would notice a striking and dominant characteristic. Its color is a deep, uniform red. This is not the vibrant, blue-white glow of youthful hot stars, but the summer crimson of stellar old age. The galaxy is what astronomers call red and dead. This seemingly simple observation unlocks one of the most fundamental puzzles in modern astrophysics. Why has this colossal, resource-rich giant essentially shut down its primary engine of creation? Why is a galaxy that resides in a bustling metropolitan cluster of thousands, surrounded by vast reservoirs of gas, no longer giving birth to new stars? The stars that paint the galaxy this deep red hue are its core population, ancient suns that formed in a glorious burst of activity billions upon billions of years ago. These are predominantly red giants and smaller, longer-lived red dwarfs. They are stellar senior citizens, having consumed the hydrogen fuel in their cores and moved into the late, stable phases of their existence. The absence of the brilliant, short-lived blue stars is the crucial clue. These massive, hot stars burn through their fuel in just a few million years, a mere blink in cosmic time. Their presence is the unmistakable signature of ongoing star formation, because if new stars are being born, a certain number of them will always be these brilliant blue giants. Their complete absence from the light of NGC 4889 tells us that the galaxy's nursery wards have been closed for business for a very, very long time, perhaps for the last 10 billion years. It's like walking into a city and finding only elderly residents. It tells you immediately that no one new has been born there for generations. This presents a profound paradox. NGC 4889 sits in the Coma Cluster, a region teeming with the raw material for star formation, hydrogen gas. This gas exists in a superheated state between the galaxies, known as the intracluster medium. Furthermore, as we saw with the lonely hydrogen cloud, fresh gas can still fall into the cluster. So, why isn't this massive galaxy, with its immense gravitational pull, actively sucking in that gas and converting it into new stars? The gravitational potential is certainly there. The answer seems to be that something is actively preventing the gas from cooling down, collapsing, and igniting into new stellar fires. The leading theories for this cosmic shutdown point to two dramatic and violent processes, one internal and one external. The internal culprit is a phenomenon known as active galactic nucleus, or AN feedback. This theory directly links the galaxy's quiescent state to the past activity of the supermassive black hole we encountered earlier. While the black hole is dormant now, in its prime it was a ferocious quasar. During that hyperactive phase, as it devoured matter, it didn't just emit light. It blasted out unimaginably powerful jets of particles and radiation, and generated intense shock waves that raced through the galaxy. This colossal output of energy would have heated the vast reservoirs of cold gas within the galaxy to incredibly high temperatures. Think of it as a celestial hairdryer blasting a cloud of water vapor, preventing the droplets from condensing and falling as rain. The AGN feedback essentially heated the galactic gas so much that it could no longer collapse under its own gravity to form stars. In a supreme irony, the very engine of the galaxy's past brilliance may have been responsible for sterilizing its future, shutting down star formation by putting the galactic gas on a permanent boil. The external mechanism is a more sinister and gradual process known as strangulation or ram pressure stripping. Imagine NGC 4889 moving at tremendous speed through the dense, hot plasma of the Coma Cluster's intracluster medium. This is not a peaceful voyage. It's like trying to walk through a hurricane. The pressure exerted by this intergalactic wind can be so powerful that it physically strips the galaxy of its own cold gas reservoir. As the galaxy plunges through the cluster, this relentless pressure acts like a cosmic squeegee, scouring away the fuel for future stars. But strangulation can be more subtle than a sudden stripping event. It can also work by removing the galaxy's extended halo of hot gas, the reservoir from which it would normally draw fresh supplies to cool and form stars over time. Without this incoming fuel, the galaxy slowly consumes what little gas it has left. Once that's gone, star formation grinds to a permanent halt. The galaxy isn't killed quickly. It's slowly starved to death, its red color a sign of a long, drawn-out fading. It's likely that both of these terrifying processes worked in tandem to create the red and dead giant we see today. The AGN feedback from the central black hole may have initially heated the gas and shut down the most vigorous central star formation. Then, as the galaxy continued its orbit through the crowded cluster center, ram pressure stripping efficiently removed any remaining gas, both the hot halo and any residual cold clouds, ensuring that there would be no recovery. This double blow left NGC 4889 as a cosmic fossil, a magnificent but static relic of an earlier, more violent era. Its continued growth now happens only through the cannibalism of other galaxies, a process that adds ancient stars but cannot spark new life. This paradox forces us to see galaxies not as isolated islands, but as dynamic entities whose fates are sealed by a complex interplay between their internal monsters and the harsh, unforgiving environments they inhabit. But the silence of this sleeping giant might be a cosmic deception, masking a phenomenon that reverberates across the very fabric of space-time itself. The violent merger history that built NGC 4889, a process we've seen evidence of in its ghostly streams and ring of globular clusters, points toward a staggering possibility deep within its core. It's conceivable that the galaxy's central supermassive black hole is not alone. Instead of a single, quiet titan, the very heart of this galaxy might be occupied by a binary system. Two supermassive black holes, each the remnant core of a galaxy that was consumed, now locked in a final, slow-motion dance of death. This potential pair would be a strange object of immense power, not emitting light but generating ripples in the universe's gravitational field, contributing to a faint cosmic hum that permeates all of space. The logic behind this idea is compelling. We know NGC 4889 grew to its immense size by devouring other galaxies. Each significant merger wouldn't just add stars, it would also deliver the smaller galaxy's own central black hole to the core of the giant. When two galaxies merge, their supermassive black holes are thought to sink toward the new common center through a process known as dynamical friction. As they travel through the dense stellar environment, their gravity slings stars away, a gravitational interaction that saps the black hole's orbital energy, causing them to spiral inward. Eventually, they would form a binary pair orbiting a common center of gravity. This is the predicted fate of such cosmic collisions, and given the sheer number of mergers in this galaxy's past, the existence of a binary black hole system at its center is not just possible, it's a highly likely outcome. The true strangeness of this object, however, lies not in its existence but in the unique type of energy it emits. As these two incomprehensibly massive objects orbit each other, they don't do so in a perfect vacuum. According to Einstein's theory of general relativity, accelerating masses and two black holes whirling around each other are the ultimate example, create ripples in the curvature of space-time itself. These ripples are gravitational waves propagating outward at the speed of light like waves on a pond. For a binary system of supermassive black holes, the waves they produce are not the high-frequency chirps detected by observatories like LIGO from stellar mass black hole mergers. Instead, they generate a persistent, low-frequency rumble, a continuous gravitational wave signal with a wavelength so long it could span light years. This is where NGC 4889 becomes a key player in a much larger cosmic symphony. The signal from one such binary, even in a relatively nearby galaxy, is too faint for our current instruments to pick out individually. But imagine every massive galaxy in the universe that has undergone a merger harbors a similar binary pair. The combined effect of millions upon millions of these supermassive black hole binaries scattered across the cosmos would create a cacophony of low-frequency gravitational waves. This collective signal is known as the stochastic gravitational wave background. It's not a distinct melody from a single source, but a steady, omnipresent hum, a background noise to the universe that carries the combined history of galactic mergers throughout cosmic time. Future observatories, specifically designed to detect these low-frequency waves, are poised to listen for this hum. Projects like the Laser Interferometer Space Antenna, or LISA, a planned space-based observatory, will use a constellation of satellites millions of kilometers apart to sense the infinitesimally small stretching and squeezing of space caused by these passing waves. When LISA finally launches, galaxies like NGC 4889 will be prime targets in the search for this background. Its well-documented history as a merger-driven supergiant makes it a blueprint for the kind of object that should be contributing significantly to this cosmic signal. By studying its properties, the masses of its central black holes and their orbital separation, astronomers can create precise models predicting the exact frequency and strength of the waves it should be producing. Detecting this background would open an entirely new window onto the universe. It would allow us to take a galactic census in a way that light cannot. We could count the number of massive black hole binaries across cosmic history, verifying our theories of how galaxies assemble themselves. Furthermore, the properties of the background hum would reveal the typical masses and merger rates of these black holes, offering unparalleled insight into the relationship between a galaxy and the monster it hosts at its center. The potential binary in NGC 4889, therefore, is more than just a strange object. It is a gravitational lighthouse, its silent, rhythmic dance encoding a story of past violence that, once we learn to listen, will tell us how the largest structures in the cosmos came to be. But the cosmic violence that left scars and relics also had a creative side, giving rise to some of the most peculiar and defiant objects in this giant galaxy. Nestled within the vast, faint stellar streams that arc around NGC 4889, astronomers have pinpointed two exceptionally bright and compact knots of light. At first glance, they might be mistaken for small, independent galaxies orbiting the giant, but a closer look reveals something far more strange. These objects are furiously giving birth to new stars, blazing with the blue-white light of youthful stellar nurseries. This is a startling sight in a galaxy otherwise known for being red and dead. The real mystery, however, isn't their vitality but their origin. These are not primordial dwarf galaxies. They are likely something much rarer and more ephemeral. Tidal dwarf galaxy candidates, celestial phoenixes born from the ashes of destruction. To understand how this rebirth happens, picture the final moments of a smaller galaxy being torn apart by NGC 4889's gravity. As the victim galaxy is stretched into long streams, it isn't just stars that get pulled out. Immense clouds of gas and dust are also stripped away. Within this collisional debris, something remarkable can occur. The chaotic forces of the merger can compress these gas clouds, triggering gravitational collapse on a colossal scale. It's a cosmic paradox. The same tidal forces that are destroying a galaxy can, in specific pockets of the wreckage, create the conditions for a new one to be born. Instead of a quiet, gradual accumulation of gas over billions of years, these objects form in a sudden, violent burst like sparks flying from a collision. They are literally built from the recycled material of their progenitor, a new stellar system emerging directly from the wreckage of an old one. The most compelling evidence that these are tidal dwarfs and not traditional galaxies comes from a profound absence. When astronomers measure their mass using the motions of their stars and gas, and then compare it to the amount of light they emit, they find a startling discrepancy. For a normal galaxy, the mass calculated from gravity is always vastly greater than the mass we can see in stars and gas. This invisible mass is, of course, the dark matter halo that holds the galaxy together. But for these two peculiar objects, the numbers align almost perfectly. The mass you can see is the mass that's there. This means these candidate tidal dwarfs appear to contain little to no dark matter. This single fact sets them apart from every galaxy that formed in the early universe, because primordial galaxies are fundamentally anchored by their dark matter skeletons. These tidal dwarfs, in contrast, are held together solely by the gravity of their own visible material, the gas and stars pulled from the merging galaxies. This lack of a dark matter halo has dramatic consequences for their long-term survival. A traditional dwarf galaxy, cocooned within its massive dark matter shield, can withstand the gravitational tides of a giant neighbor for eons. But a tidal dwarf galaxy is a fragile creature. Without that invisible gravitational reinforcement, it is far more vulnerable to being torn apart again by the very forces that created it. Its future is uncertain. It might survive as a coherent object for a few billion years, or it might be short-lived, its stars destined to be scattered back into the halo of NGC 4889. Their existence is a testament to the dynamic, cyclical nature of the cosmos, where destruction and creation are often two sides of the same coin. They are living proof that even in the aftermath of galactic chaos, the universe can find a way to forge new islands of stars from the debris of the old. But the evidence for past mergers in NGC 4889 becomes even more spectacularly complex when we zoom into its very heart. Among the most baffling observations is the detection of not one, not two, but three distinct, intensely bright nuclei clustered near the galaxy's center. Each of these brilliant points of light behaves like a miniature quasar, a signature of an active supermassive black hole feeding on surrounding material. This is the potential signature of a triple AGN, or active galactic nucleus, a celestial configuration so rare and unstable that it represents one of the most extreme environments in the known universe. The idea of three supermassive black holes, each weighing millions or even billions of times the mass of our Sun, all vying for dominance in a region of space not much larger than our own solar system, stretches our understanding of galactic dynamics to the breaking point. The formation of such a system is a direct consequence of the galaxy's gluttonous history. We've already seen how NGC 4889 grew by consuming smaller galaxies. Normally, when two galaxies merge, their central black holes are expected to eventually spiral together and coalesce into a single, larger black hole. But what happens if a third galaxy enters the fray before the first pair has had time to merge? The result is a chaotic gravitational ménage à trois. Imagine a galactic merger is underway and the two central black holes are in the slow process of inspiral. Suddenly, a second merger event occurs, delivering a third supermassive black hole into the already tumultuous core. Instead of an orderly dance, you get a gravitational free-for-all, a cosmic mosh pit where three titans are thrown together, each pulling on the others with unimaginable force. The dynamics within this triple system are anything but peaceful. The black holes would engage in a complex gravitational dance, their orbits constantly shifting due to their mutual interactions. This isn't a stable, predictable configuration like planets orbiting a star. It's a chaotic system where close encounters can fling one of the black holes into a wildly different orbit or even eject it from the galactic center entirely. The most likely outcome of such a setup is the eventual ejection of the lightest black hole. Through a process known as the slingshot effect, a close pass between two of the heavier black holes can transfer a tremendous amount of kinetic energy to the third, lighter one, catapulting it out into the galactic halo at speeds of thousands of kilometers per second. This would leave behind a more stable binary system, which might then eventually merge. The presence of 3 bright nuclei suggests we might be catching this system in a fleeting, transient state, a cosmic snapshot of a gravitational argument that has not yet been resolved. The environment around these 3 monsters would be a realm of pure gravitational fury. Stars unfortunate enough to wander into this region would be subjected to extreme tidal forces, their paths twisted into chaotic orbits. Some stars would be violently ejected as hypervelocity stars, much like we discussed earlier, but with even greater speeds thanks to the combined kick from multiple black holes. Others might be torn apart entirely, their material feeding the bright accretion disks that make the nuclei visible. The space around the triple AGN would be crisscrossed by these stellar projectiles and shrouded in the intense radiation from 3 separate feasting events, creating a zone of unparalleled astrophysical violence. The ultimate fate of such a system holds the promise of detecting the most powerful events since the Big Bang. If the black holes do eventually merge rather than ejecting one another, the resulting gravitational wave signal would be monumental. A merger involving 2 supermassive black holes is already a supremely energetic event, but a triple merger could produce gravitational waves of an even more complex and intense character. While the triple AGN in NGC 4889 is a testament to past violence, it also points toward a future cataclysm that would ripple across the cosmos, a definitive announcement that even the largest structures in the universe are subject to change. Moving beyond the chaotic core and its potential triple black hole system, our journey through the strange objects of NGC 4889 takes us to a structure of such immense scale and subtle glow that it challenges the very definition of an object. Hovering in the space around the galaxy is a Lyman alpha blob, a cosmic enigma whose name barely hints at its profound mystery. This is not a solid body or a distinct galaxy, but a colossal, amorphous cloud of hydrogen gas, millions of light years across, that is glowing with a specific, faint hue of ultraviolet light known as Lyman alpha radiation. Under normal circumstances, such a glow is a clear signpost of tremendous energy, a beacon for intense star formation or the ferocious activity of a feeding black hole. But this particular blob presents a confounding puzzle. It is shining brightly in the profound emptiness, far from any visible source of power that could possibly be causing its illumination. To understand why this is so strange, we need to understand what Lyman alpha radiation signifies. It's a very specific fingerprint of hydrogen, the universe's most basic element. When an electron in a hydrogen atom gets excited typically by absorbing energy from a nearby source, it can jump to a higher energy level. When that electron falls back down to its regular state, it releases that energy as a photon of light at a very precise wavelength. This is the Lyman alpha line. For a vast cloud of hydrogen to glow in this way, something must be energizing it, like a blacklight making a poster fluoresce. The most common culprits are starburst galaxies, where millions of young, hot stars flood their surroundings with ultraviolet light, or active galactic nuclei, where the intense radiation from an accretion disk does the same job. But in this case, when astronomers search the heart of the blob for such an engine, they find nothing but darkness. The blob is an enormous, glowing ghost with no visible lamp. This has led scientists to propose some truly fascinating theories to explain the blob's mysterious light. One compelling idea is that the energy source is indeed present, but it is hidden from our view. Perhaps at the very center of this glowing cloud lies a heavily obscured quasar, a supermassive black hole in the midst of a feeding frenzy. If the black hole is surrounded by an incredibly thick, donut-shaped ring of gas and dust, a structure known as a torus, our optical and X-ray telescopes might not be able to see the brilliant core directly. The torus would absorb most of the quasar's intense light, but the Lyman alpha radiation, being a specific emission from the surrounding hydrogen, could still escape, effectively outlining the hidden monster in a soft, ultraviolet glow. It would be like seeing the glow from a street lamp through a dense fog. You can't see the bulb itself, but you can clearly see the halo of light it creates in the mist. Another, more exotic explanation involves the violent environment of the galaxy cluster itself. NGC 4889 is not floating in empty space. It is moving at tremendous speed through the superheated plasma that fills the Coma Cluster, the intracluster medium. As the galaxy plows through this thin but searingly hot gas, it could be generating immense shock waves. These shocks would compress and heat the hydrogen gas in the galaxy's extended halo, potentially causing it to glow with Lyman alpha radiation. In this scenario, the blob is not a sign of internal creation, but a symptom of external violence, a cosmic wake glowing behind the galaxy as it hurtles through its cluster. The energy for the light comes not from stars or a black hole, but from the sheer kinetic energy of the galaxy's motion, a colossal friction heating the gas to the point of emission. A third, and perhaps most profound, possibility is that we are witnessing the slow, gentle cooling of the primordial gas that pervades the cluster. The intracluster medium is incredibly hot, but over astronomical timescales, it can slowly radiate away its heat and condense. As the gas cools, it could be releasing energy in the form of this specific ultraviolet light. If this is true, the Lyman alpha blob is a snapshot of a fundamental cosmic process, the gradual settling and cooling of the raw material of the universe, a process that might eventually lead to the formation of new galaxies or the fueling of existing ones. This would make the blob a cosmic reservoir in the act of condensing, its gentle glow a signature of transformation on a scale almost too large to comprehend. Each of these theories paints a dramatically different picture of the blob's nature and origin. Is it the cloak of a hidden quasar, the fiery wake of a speeding giant, or the cooling breath of the cluster itself? The answer lies in the detailed properties of the light it emits. By analyzing the exact spectrum and the shape of the blob, astronomers can search for clues. If the light shows signs of being energized by a powerful, point-like source, the hidden quasar theory gains strength. If the emission is smooth and extended, aligning with the galaxy's direction of motion, the shock wave hypothesis becomes more likely. This strange, ethereal object, therefore, is more than just a cloud. It is a natural laboratory for studying some of the most energetic processes in the universe, its faint light holding the key to understanding the hidden dynamics of galaxy clusters and the life cycles of the gas that binds them together. But even with the potential for a triple black hole system or a hidden quasar energizing a Lyman alpha blob, the true enigma at the heart of NGC 4889 remains the staggering mass of its primary supermassive black hole. You might think that the most massive galaxies in the universe would naturally host the most massive black holes, and to a large extent that's true. There is a well-established correlation, a cosmic rule of thumb, that links the mass of a galaxy's central bulge of stars to the mass of the black hole it contains. It's a relationship that points to a shared history, a co-evolution where the growth of the galaxy and the growth of its central monster are fundamentally intertwined. But the black hole in NGC 4889 isn't just large, it's an outlier, a rule breaker. Its colossal 21 billion solar mass figure is disproportionately huge, even for a supergiant galaxy of this scale. This is what astronomers call an overmassive black hole, an object whose sheer size pushes against the boundaries of our theoretical models and hints at a formation story far more violent than we ever imagined. To grasp just how unusual this is, let's put it in perspective. Our Milky Way's central black hole, Sagittarius, a star, has a mass of about 4 million suns. The mass of the Milky Way stellar bulge is roughly 25 billion solar masses. This gives a ratio where the black hole is about 0.1% of the bulge's mass. Now consider NGC 4889. While its total stellar mass is immense, its bulge-to-black hole ratio is significantly higher. Its black hole represents a much larger fraction of the galactic core's mass than the standard correlation would predict. It's as if you found a tiny village with a skyscraper designed for a metropolis. The scale is simply out of sync with its surroundings. This discrepancy forces us to ask a critical question. Did this black hole grow too fast, or did the galaxy around it somehow fail to keep up? The leading explanation points to a uniquely voracious and efficient feeding frenzy in the distant past. The standard model of co-evolution suggests a relatively steady, regulated growth. Gas flows into the galactic center, fueling both star formation in the bulge and accretion onto the black hole. The black hole's subsequent outbursts, its AGN feedback, then regulate that growth by heating the gas and slowing down further star formation. It's a balanced, self-limiting process, but for NGC 4889, this balance may have been shattered. Perhaps this galaxy experienced an exceptionally rich and sustained inflow of cold gas very early in its history. This could have been triggered by a major merger that funneled a vast amount of material directly into the core, creating a perfect storm of accretion. The black hole would have entered a phase of super-efficient feeding, gobbling up matter at a rate approaching its theoretical limit, a state known as super-Eddington accretion. During this period, it could have packed on billions of solar masses in a relatively short cosmic time, far outpacing the growth of the stellar bulge around it. Another fascinating possibility involves the nature of the gas it consumed. What if the material falling into the black hole wasn't typical interstellar gas, but was instead composed largely of dark matter and low-mass stars? These components contribute to gravity but do not shine brightly. If the black hole grew primarily by consuming such dark material, the surrounding bulge of luminous stars would not have needed to grow at the same proportionate rate to explain the gravitational forces at play. The black hole's mass would be high, but the visible stellar signature we use to measure the galaxy's bulge would be comparatively lower, creating the illusion of an overmassive ratio. This idea suggests that the diet of a black hole can dramatically influence its final place on the cosmic scale. The environment of the Coma Cluster itself might be the ultimate key to this mystery. As the central dominant galaxy in a dense cluster, NGC 4889 holds a privileged position. It sits at the bottom of the cluster's gravitational well, meaning that any gas that cools from the hot intracluster medium will naturally flow down toward it. This provides a continuous, albeit slow, supply of fuel that other galaxies might not enjoy. Over billions of years, this trickle feeding could have allowed its black hole to accumulate more mass than a similar galaxy in a less dense environment. Its location as the king of its cosmic city guaranteed it a larger portion of the available resources, enabling its central black hole to become the heavyweight champion we observe today. This overmassive black hole is more than just a curiosity. It's a challenge to the universality of the black hole-galaxy scaling relations. Its existence tells us that while these correlations are a good guide for most galaxies, the most extreme environments can produce extreme outliers. These outliers are not mistakes, they are crucial data points that reveal the different pathways a galaxy can take. NGC 4889, with its record-breaking black hole, stands as a monumental example of a galaxy that took the path of unchecked, gluttonous growth, a testament to a uniquely violent and efficient accretion history that has left an indelible mark on the very heart of this cosmic leviathan. Now, if we pull our focus back from the immense mass of the central black hole and look at the broader core of the galaxy, we encounter a different kind of puzzle, one written in the frantic motion of the stars themselves. The very heart of NGC 4889, a region spanning a few thousand light-years, is a scene of incredible stellar chaos. Unlike the orderly, rotating disk of a spiral galaxy like our own, where stars follow placid, circular orbits, The stars here are moving at breakneck speeds in what appears to be a completely random, frenzied dance. They zip past one another on wildly elliptical paths, some rushing directly toward us while others hurtle away, all trapped in the overwhelming gravitational grip of the galactic center. This chaotic motion is a phenomenon astronomers call a high-velocity dispersion, and measuring it is one of the most direct ways we have to weigh the monster lurking at the core. The principle behind this is beautifully simple and is rooted in the same basic physics that allows us to weigh the Sun by observing Earth's orbit. A star's velocity is a direct response to the gravitational pull it feels. The faster a star is moving, the stronger the gravity must be to keep it from flying off into space. By carefully measuring the speeds of thousands of individual stars in the galactic core, using the Doppler shift of their light to see if they are moving toward us, blue-shifted or away from us, red-shifted astronomers can calculate the total mass contained within their orbits. It's like being able to determine the weight of a black hole by watching how fast the stars around it are whirling. When they performed this measurement for NGC 4889, the result was staggering, confirming the presence of a gravitational anchor of almost unimaginable proportions, perfectly aligning with the 21 billion solar mass black hole we've already discussed. But the plot thickens considerably when we compare these observations to our most sophisticated computer simulations. The models, which incorporate our best understanding of gravity and stellar dynamics, predict a certain level of velocity dispersion for a galaxy with a black hole of this mass. The strange part is that the actual observed chaos in the core of NGC 4889 is even more extreme than the models suggest it should be. The stars are moving faster on more erratic paths than the presence of the central black hole alone can easily explain. This discrepancy is a tantalizing clue, a sign that there is more to the story of this galactic core than just a single quiet titan. The velocity dispersion is like a fingerprint, and the smudges in that fingerprint point to two fascinating possibilities. The first explanation involves the ghost of mergers past. We know this galaxy has a history of cannibalism, and the central region is the ultimate repository for the debris of those collisions. When smaller galaxies are consumed, their stars don't just quietly assimilate, they are injected into the core on new, often highly energetic orbits. This infusion of stars from multiple directions, each with its own unique velocity imparted by the merger event, could be supercharging the core's dispersion, stirring the stellar population into a more frantic state than if the galaxy had grown in peaceful isolation. It's the difference between a calm pond and one that has just had several large stones thrown into it. The ripples and splashes create a much more turbulent and unpredictable environment. The high-velocity dispersion, in this view, is the lingering echo of ancient galactic violence, a dynamical fossil that has not yet had time to settle down. The second and more provocative idea is that we are seeing the gravitational signature of something unseen adding to the mix. While the supermassive black hole dominates the gravity in the very center, its influence weakens with distance. The unexpectedly high velocities of stars a bit further out could be indicating an additional source of mass concentrated in the core region. This could be a dense cusp of dark matter, a concentration of the invisible substance that is even more packed toward the center than our standard models predict. Alternatively, and this connects back to the earlier mystery, it could be the gravitational footprint of a second or even third supermassive black hole. If a binary or triple black hole system is indeed present, their complex gravitational interactions would violently perturb the orbits of nearby stars, kicking them to higher speeds and creating precisely the kind of elevated velocity dispersion we observe. The frantic dance of the stars, therefore, might not just be a measure of a single mass, but a reflection of a gravitational argument still raging at the very heart of this galactic giant. Yet even the chaotic stellar dance at the galaxy's core cannot contain every object forever. and our journey now takes us to one of the most poignant and isolated sites in the entire cluster. Drifting in the profound emptiness between galaxies, far from the familiar glow of any stellar city, is a single, delicate cosmic bubble known as a planetary nebula. This is not a planet despite the historical misnomer. It is the final, beautiful breath of a dying star. For billions of years, a star much like our own Sun lived a quiet life, fusing hydrogen in its core. But as it reached the end of its life, it swelled into a red giant and then gently shrugged off its outer layers, creating a vast, expanding shell of incandescent gas. What makes this particular nebula so strange is its location. It is floating freely in the intracluster space, a lone, glowing ember in an ocean of darkness, yet its motion reveals it is still gravitationally tethered to the immense pull of NGC 4889. The existence of this isolated object tells a dramatic story of stellar ejection. This aging star did not die in the peaceful suburbs of its home galaxy. Instead, it was violently evicted. The most likely scenario involves a gravitational encounter so extreme it amounts to a cosmic slingshot. Imagine this star, then part of a binary system, drifting too close to the dense core of NGC 4889. The complex gravitational pull from the central supermassive black hole, or perhaps from a dense cluster of stars, could have disrupted the binary pair. In a flash of orbital energy, one star might have been captured, while the other, the progenitor of our nebula, was flung out of the galaxy entirely at high speed. It then spent millions or billions of years traveling through the intergalactic void, a solitary wanderer, until the very end of its life when it ignited its own funeral shroud. The planetary nebula we see is the ghost of a star that died far from home, its glowing shell a testament to a journey that began with a gravitational catastrophe. Studying the light from this ejected nebula provides astronomers with a rare and valuable opportunity. The specific colors and emission lines in its spectrum act as a forensic chemical analysis, revealing the exact composition of the gases that were once deep inside the star. This is like being able to perform an autopsy on a star that belonged to a different galactic environment. When we compare the chemical fingerprint of this intracluster planetary nebula to those found within galaxies like our own Milky Way, we sometimes find subtle but significant differences. The abundances of elements like oxygen, nitrogen, and argon can tell us about the star's initial composition, which in turn reflects the chemical environment of its birthplace within NGC 4889 billions of years earlier. This lone beacon therefore becomes a messenger from a foreign stellar population. Stars that form in different types of galaxies, in massive ellipticals versus smaller spirals, for instance, can inherit different chemical signatures from the gas clouds that birthed them. By analyzing this ejected nebula, we are essentially sampling the chemical history of NGC 4889 itself, without having to untangle the complex light of billions of other stars. Its isolation makes it a pristine laboratory. If its composition shows an overabundance of certain elements formed in previous generations of stars, it would suggest that the environment in NGC 4889 was exceptionally efficient at enriching its gas with heavy elements early in its history, corroborating the picture of a galaxy that experienced intense, rapid star formation in its youth. The future of this beautiful, lonely object is one of gradual dissolution. The expanding shell of gas, already incredibly tenuous, will continue to drift outward. Over the next several tens of thousands of years, it will mix with the even more diffuse gas of the intracluster medium, its atoms scattering until they become indistinguishable from the background. The central white dwarf remnant of the star will cool and fade over billions of years, eventually becoming a cold, dark crystal of carbon and oxygen. This intracluster planetary nebula is thus a fleeting monument, a temporary marker of a star that lived, died, and journeyed through the vastest emptiness imaginable. Its brief, brilliant glow illuminates not just the processes of stellar death, but also the dynamic gravitational forces that can fling stars into the intergalactic darkness, creating solitary waypoints in the immense architecture of the cosmos. And here we encounter a feature that seems almost out of place in the smooth, rounded form of this elliptical giant, a prominent dark lane of cosmic dust. In a spiral galaxy like our own, such dust lanes are expected, winding through the starry arms. But in a vast elliptical galaxy like NGC 4889, which should be a relatively simple, three-dimensional swarm of ancient stars, the presence of any distinct dust lane is noteworthy in itself. This one cuts across the galaxy's face like a dark scar, a reminder that this serene-looking giant has a violent and messy history. The real mystery, however, isn't its existence, but its bizarrely warped and twisted shape. Instead of lying in a neat, symmetrical plane, this dust lane is decidedly lopsided, bent and distorted in a way that tells us the galaxy's interior is anything but a quiet retirement home for old stars. The origin of this dust is almost certainly external. NGC 4889, as we've learned, is a cannibal. It grew by consuming smaller, gas-rich galaxies. When such a galaxy is torn apart and absorbed, it doesn't just contribute stars, it also donates all of its interstellar material, immense clouds of gas and dust. This newly acquired dust should, theoretically, eventually settle into the galaxy's core, driven by gravity and friction to form a stable, rotating disk. The fact that it hasn't done so, that it remains in this chaotic, asymmetric lane, is a clear sign that something is actively preventing it from reaching equilibrium. The dust is like smoke in a room that refuses to settle, stirred by unseen currents and forces. One of the most likely culprits for this ongoing disturbance is the sheer violence of the galaxy's own stellar environment. The core of NGC 4899 is a maelstrom of stellar motion, with stars whizzing past on random, high-speed orbits. As this dusty debris tries to settle, it's constantly being jostled and buffeted by the gravitational wakes of these passing stars. It's akin to trying to smooth out a sheet on a bed while people are still jumping on the mattress. The gravitational turbulence within the galaxy itself could be enough to keep the dust from ever forming a calm, organized disk, instead twisting it into the warped lane we observe. But there's another, more external force that could be at play, the immense pressure of the intracluster medium. Remember, NGC 4889 is not sailing through empty space. It's moving at phenomenal speed through the superheated, thin plasma that fills the Coma Cluster. This intergalactic wind exerts a powerful ram pressure on the galaxy. For the dust lane, which is a relatively fragile structure, this constant headwind could be physically pushing it, distorting its shape and preventing it from settling into a stable orientation. The asymmetry of the lane, therefore, might act as a cosmic weather vane, indicating the direction from which this intergalactic gale is blowing. The dust is not just tracing the galaxy's past acquisitions, it's also mapping the present-day forces acting upon it from the outside. This persistent asymmetry makes the dust lane far more than a simple curiosity. It serves as a dynamic probe of the conditions inside the galaxy. By studying the exact shape and degree of the warp, and by measuring the motions of the dust clouds using radio telescopes, astronomers can infer the strength of the internal gravitational turbulence. They can essentially use the dust as a tracer to measure the invisible gravitational pushes and pulls that are otherwise impossible to see directly. Furthermore, the composition of the dust itself, analyzed through the specific wavelengths of light it absorbs, can reveal the chemical fingerprint of the galaxy that was consumed, telling us something about the nature of the victim that donated this material billions of years ago. This strange, twisted lane is a testament to the fact that even after a merger is complete, the aftermath can continue to shape a galaxy for eons, a visible signature of dynamical processes that are still very much alive within this ancient cosmic giant. Moving out from the galaxy's turbulent core, our search for strangeness leads us to two brilliant, point-like pinpricks of extreme energy. These are not the faint, scattered X-ray binaries we discussed earlier, nor are they the singular, monstrous output of the central black hole. Instead, they are a pair of what astronomers classify as ultraluminous X-ray sources, or ULCs. The name itself gives away their primary mystery. They are ultra-luminous, shining with a ferocious X-ray brightness that defies easy explanation. To grasp just how peculiar they are, consider that a typical stellar mass black hole or neutron star, feeding at its theoretical maximum, has a well-defined brightness limit called the Eddington limit. This is the point where the intense radiation pressure from the accretion process pushes back against the infalling matter, creating a balance that caps the object's luminosity. Yet these two sources in NGC 4889 blast out X-rays at levels that can be hundreds, even thousands of times greater than this established limit for a stellar mass object. They are cosmic overachievers, shining with an intensity that, according to our standard textbooks, simply shouldn't be possible. This glaring contradiction has sparked a vigorous and fascinating debate among astrophysicists, centered on a fundamental question: what kind of engine could possibly power such an outrageous output? The leading theories propose three radically different solutions, each with profound implications. The first, and perhaps most tantalizing, idea is that we are finally looking at strong evidence for the long-sought intermediate mass black holes. Think of these as the missing link in the black hole family. We have well-documented stellar mass black holes weighing up to several dozen times the mass of our Sun, and we have the supermassive giants like the one at the galaxy's center weighing billions of solar masses. But the existence of black holes in the middle ground between 100 and 100,000 solar masses has been much harder to confirm. If one of these ULXs is powered by an intermediate mass black hole, the luminosity puzzle solves itself neatly. A more massive black hole has a higher Eddington limit. It can accrete matter at a higher rate and shine brighter without blowing its own fuel supply away. Finding one would be a monumental discovery, filling a crucial gap in our understanding of how the largest black holes grow from the remnants of the first stars. A second, more recent theory challenges this elegant solution with an even more bizarre proposition. What if the power source isn't a black hole at all, but a neutron star? Neutron stars are the incredibly dense, city-sized cores left behind after a supernova, and they have magnetic fields of almost unimaginable strength. For decades, we thought their brightness was also capped by the Eddington limit, but recent observations of ULXs in other galaxies have astonishingly revealed that some of them are indeed powered by neutron stars. How is this possible? The answer may lie in those immensely powerful magnetic fields. A neutron star with a magnetar level field could have a completely different accretion geometry. The magnetic field might funnel the infalling material directly onto the star's magnetic poles, creating incredibly hot, focused columns of plasma that shine with X-rays. In this scenario, the apparent violation of the Eddington limit is an illusion. The emission isn't spreading out in all directions, but is beamed into narrow jets like a cosmic lighthouse. If we happen to be looking straight down the beam, the source appears far brighter than it truly is overall. The third possibility is a variation on this beaming theme, but applied to a more common stellar mass black hole. Perhaps through some complex and unstable accretion process, the material falling in forms a thick, dense disk that funnels the resulting radiation into a cone. Again, if that cone is pointed directly at Earth, we would measure an artificially high luminosity. This makes determining the true nature of any ULX incredibly tricky, as its appearance depends heavily on our perspective. The challenge with the two sources in NGC 4889 is that they are so distant, resolving the fine details needed to distinguish between these models, Like measuring tiny fluctuations in their brightness or detecting the signature of a neutron star's spin pushes our current telescopes to their absolute limits. The presence of these ULXs in this specific galaxy adds another layer of intrigue. Their environment might be the key to their extreme behavior. The core of NGC 4889 is a densely packed stellar environment, a place where close encounters and gravitational interactions are common. It's possible that these ULXs are in binary systems where the donor star is overflowing its Roche lobe at an exceptionally high rate, providing a fire hose of fuel that allows the compact object to accrete at a supercritical rate, temporarily blowing past its Eddington limit in a spectacular outburst. Alternatively, the donor star itself might be an unusual type, like a massive, evolved star, shedding its outer layers in a dense wind that is then captured and devoured by its dense companion. Each scenario represents a different pathway to extreme luminosity, and studying these two specific sources helps astronomers refine the conditions necessary to create such extraordinary objects. They are not merely curiosities. They are natural experiments that force us to test and expand our understanding of how matter behaves under the most extreme gravitational stresses imaginable. This galactic cannibal has left its fingerprints not just in the scattered streams of its victims, but also in a series of remarkably elegant and subtle patterns imprinted on its outermost halo. If you could process the faint starlight of NGC 4889 to remove its bright central glow, you would witness an astonishing sight, a set of faint, concentric shells of stars, stacked one inside the other like the layers of a cosmic onion or the ripples from a stone dropped into a pond. These are not solid structures but vast, ghostly arcs, each composed of millions of stars moving in concert. They curve gracefully through the darkness, marking the furthest reaches of the galaxy's gravitational domain. Unlike the chaotic streams from smaller, gas-rich galaxies, these shell structures are the distinctive signature of a very specific type of galactic encounter, a dry merger. A dry merger is the cosmic equivalent of a corporate merger between two established companies, rather than a startup being acquired. It occurs when two large, elliptical galaxies, which have both already exhausted their cold gas reserves and ceased forming new stars, collide and combine. Since there's little gas present, the merger doesn't trigger any brilliant bursts of new star formation. It's a quiet, stellar affair. The violence is purely gravitational. When such a gas-poor galaxy is consumed, its stars don't get scattered randomly. Instead, they are stripped away and then, in a beautiful and complex gravitational dance, they begin to oscillate back and forth through the center of the dominant galaxy. The key to understanding the shells lies in this oscillation. Imagine the stars from the victim galaxy being pulled inward by gravity, gaining speed as they fall toward the center. They don't stop there, they swing right through to the other side, slowing down as they climb back out against gravity, only to fall back in again. At the outermost points of their orbits, at the turning points where their radial motion momentarily stops, they naturally pile up. It is at these apocenters that the starlight becomes concentrated, creating the faint, sharp-edged shells we observe. The real power of these shells, however, is that they act as a celestial clock. The number of visible shells and the spacing between them are not random. They are direct products of the mass of the host galaxy and the time that has elapsed since the merger. Think of it like watching ripples on a pond after a stone is thrown in. The initial splash creates a set of ripples that move outward. Over time, the ripples spread farther apart and gradually fade away. In a galaxy, the splash is the merger event. Computer simulations show that the more time that has passed, the fewer shells we will see, as the outermost ones have had time to travel further and become too faint and diffuse to detect. The spacing between the shells also increases with time. By carefully counting the shells around NGC 4889 and measuring the distances between them, astronomers can essentially rewind the simulation. They can adjust the parameters until their model reproduces the exact pattern we see today, and in doing so, they can pin down a remarkably precise date for the collision. For NGC 4889, the evidence written in these stellar ripples points to a relatively recent merger in astronomical terms, likely occurring within the last 1 to 2 billion years. This might seem like an immense stretch of time, but for a galaxy over 10 billion years old, it's a recent event, a chapter that concluded long after dinosaurs roamed Earth but well before humans appeared. This timeline is crucial because it tells us that this supergiant galaxy did not finish its growth in the ancient past. It has been actively under construction for most of the universe's history, right up to a point we consider cosmically modern. The presence of these sharp, well-defined shells indicates that there hasn't been enough time for subsequent gravitational interactions to smear them out, meaning this was one of the last major acquisitions in this giant's long history of consumption. Beyond just dating the event, the shells provide a unique way to weigh the galaxy itself. The oscillation of the stars that creates the shells is governed by the galaxy's gravitational potential, the combination of the pull from all its stars and its dark matter halo. The speed at which stars complete their orbital journey from one shell to the next depends directly on the total mass they are orbiting within. By analyzing the shell spacing and dynamics, astronomers can derive an independent measurement of NGC 4889's mass, offering a valuable check against other methods like gravitational lensing or stellar velocity dispersion. This makes the shells more than just a fossil record. They are an active gravitational probe, their elegant geometry serving as a precise tool for measuring the invisible forces that shape the cosmos. In their faint, silent arcs, we find a detailed history of a violent encounter and a dynamic map of the immense power that holds this galactic titan together. This brings us to a profound and central mystery that underpins the very nature of this supergiant galaxy, a strange object defined by its absence. Despite its colossal size and immense gravitational pull, NGC 4889 is missing something fundamental: vast, cold reservoirs of molecular gas. This is the cosmic equivalent of finding a sprawling, advanced metropolis with towering skyscrapers and a vast population, but with no farms, no warehouses of raw materials, and no factories to build anything new. The raw material for creating new stars is simply not there in any significant quantity. This absence is the ultimate explanation for its red and dead state, but it presents a major puzzle. Why would a galaxy with such a powerful gravity not be able to hold onto or attract the very stuff that built it in the first place? The surprise deepens when we compare NGC 4889 to other giant elliptical galaxies in the universe. Not all of them are completely gas-poor. Some, particularly those that exist in quieter, less dense regions of space, have managed to retain substantial reservoirs of cold hydrogen gas, often arranged in a large rotating disk. These gas-rich ellipticals are the exception, not the rule, but their existence proves that it is possible for a massive elliptical to hold onto its fuel. This comparison makes the situation of our subject galaxy even more striking. It's not simply that all giant ellipticals naturally run out of gas. Something specific must have happened to NGC 4889. An environmental factor or a violent event that efficiently and thoroughly scoured it clean. The prime suspect in this cosmic mystery is a relentless external force known as ram pressure stripping. To understand this, you need to picture the environment NGC 4889 calls home, the heart of the Coma Cluster. This is not empty space. It's filled with a superheated, thin plasma called the intracluster medium, which can reach temperatures of tens of millions of degrees. As the galaxy moves at incredible speed through this cluster, at over 1,000 kilometers per second, it doesn't glide peacefully. It plows through this searing gas, and the effect is like holding a delicate piece of fabric out of the window of a speeding car. The intracluster medium exerts a powerful, continuous pressure on the galaxy's own gas reservoir. For the cold, dense clouds of molecular gas that are the birthplaces of stars, this pressure is catastrophic. They are not gravitationally bound tightly enough to withstand this relentless cosmic headwind. One by one, these gas clouds are literally ripped away from the galaxy, like leaves being torn from a tree in a hurricane and swept out into the intercluster void. This process would have been incredibly efficient over the billions of years that NGC 4889 has been orbiting the cluster center. It's a form of gradual starvation. The galaxy isn't just using up its gas, it's having its future sustenance violently stripped away before it can even be consumed. The strangest part of this mechanism is its selectivity. Ram pressure stripping is most effective against the diffuse cold gas. The stars, being vastly more massive and compact, are largely unaffected by this intergalactic wind. So, the galaxy can retain its trillion-star population while having the gaseous fuel for the next generation systematically removed. It's a process that leaves the stellar city intact but ensures it has no way to grow or renew itself, effectively fossilizing the galaxy in its current state. However, Ram pressure stripping might not be the only culprit. It's highly likely that this external force worked in tandem with the galaxy's own internal monster. We discussed earlier the concept of AGN feedback from the central supermassive black hole. During its active quasar phase, the black hole would have blasted the galaxy with unimaginable energy, heating the remaining cold gas to such high temperatures that it could no longer collapse to form stars. This internal heating would have made the galaxy's gas much more vulnerable to the external stripping. Imagine the gas being first puffed up and pressurized from the inside by the AGN, making it less dense and more diffuse, and then the Ram pressure wind from the cluster finds it much easier to sweep this loosened material away. The two processes could have acted as a devastating one-two punch, first sterilizing the galaxy from within, and then efficiently removing the evidence, leaving behind the gas-poor giant we observe today. This missing cold gas is more than just an explanation for a lack of new stars. It's a critical clue to the life cycle of galaxies in the most extreme environments. NGC 4889 stands as a stark example of a galaxy whose fate was sealed not just by its own internal evolution, but by the harsh, unforgiving neighborhood it resides in. Its emptiness is a direct result of its privileged yet perilous position as the central dominant galaxy in a massive cluster, a testament to the fact that in the cosmos, location is everything, and even the mightiest giants can be starved into quiescence by the forces that surround them. Yet even in this vast retirement home for ancient stars, where the dominant color is the deep crimson of stellar old age, there exists a population of celestial rebels that defy the narrative of a quiet, fading giant. Scattered across the core of NGC 4889 are brilliant blue-white stars that stand out like dazzling sapphires against a background of somber rubies. These are not the expected, short-lived blue giants that signal new star birth. That process ended billions of years ago. Instead, these are blue stragglers, stellar anomalies that appear paradoxically youthful and vibrant amidst their elderly neighbors. Their very existence presents a delightful cosmic contradiction. How can a galaxy that is no longer making new stars still contain stars that look so brilliantly young? The secret to their rejuvenation lies not in being born late, but in a dramatic second act. These stars are ancient, just like all the others, but they have found a way to cheat stellar evolution. A normal, sun-like star follows a predictable life cycle, spending most of its existence burning hydrogen in its core before eventually swelling into a red giant. More massive stars burn hotter and bluer, but they also exhaust their fuel much more quickly. In a population of stars that all formed at roughly the same time billions of years ago, all the massive blue stars should have burned out long ago, leaving behind only the slower-burning, cooler, redder stars. The presence of blue stragglers means that some stars have somehow acquired a fresh supply of hydrogen fuel, allowing them to reignite their nuclear furnaces and masquerade as much younger, more massive stars. There are two primary and equally violent pathways for this stellar rebirth, both of which are perfectly suited to the extreme environment at the heart of NGC 4889. The first is a direct stellar collision. In the incredibly dense core of this supergiant galaxy, stars are packed together much more tightly than in our own galactic neighborhood. The probability of two stars actually colliding while still astronomically low becomes significantly higher in such a crowded space. When two lower mass aging stars collide, they can merge into a single, more massive object. This new combined star has a larger core and a fresh outer layer of hydrogen fuel. It effectively resets its evolutionary clock, beginning a new life as a hotter, bluer, and more luminous star than either of its progenitors. It's a cosmic phoenix born from the fiery merger of its former selves. The second pathway involves a slower, more intimate dance between a binary star system. Many stars in the galaxy are born in pairs orbiting a common center of gravity. Over time, as one star evolves and begins to swell into a red giant, it can transfer its outer hydrogen envelope onto its smaller, denser companion. The receiving star gains mass and, just like in a collision, is rejuvenated, becoming a blue straggler. In some cases, the two stars might even spiral together and merge completely. These binary interactions are likely the more common formation method, acting as a slow-motion fountain of youth for stars locked in a gravitational embrace. The intense conditions within NGC 4889 make it a perfect breeding ground for these stellar rebels. The same high stellar density that contributes to the chaotic velocity dispersion we discussed earlier also increases the frequency of both direct collisions and the gravitational encounters that can perturb binary systems, driving them toward merger. The blue straggler population, therefore, is a direct consequence of the galaxy's crowded core. They are a shimmering signature of the dynamic violence that continues to occur even in a galaxy that is otherwise evolutionarily dormant. They prove that while star formation may have ceased, the galaxy is far from static. It is a place where ancient stars are constantly interacting, colliding, and merging, creating brilliant exceptions to the rule of stellar aging. Studying these blue stragglers offers astronomers a unique way to probe the dynamical history of the galactic core. The number and distribution of these stars serve as a fossil record of the core's density over time. A higher concentration of blue stragglers suggests an environment that was, or still is, exceptionally crowded, favoring the interactions that create them. By mapping their locations, scientists can gain insights into how the stellar population in the core has been stirred and shaped by gravitational forces, including the potential influence of a central black hole binary. These seemingly youthful stars are more than just pretty anomalies. They are vital diagnostic tools, their blue light illuminating the ongoing gravitational drama at the heart of this sleeping giant. But even as we observe these individual stellar anomalies, the most profound evidence of this galaxy's violent history is written not in single stars, but in the very spin of its heart. Deep within the central region of NGC 4889, astronomers have uncovered a phenomenon of almost architectural complexity, not one but three distinct kinematically decoupled cores. Imagine a galaxy as a vast, swirling whirlpool of stars. Now picture within that whirlpool three smaller, separate whirlpools, each spinning on its own axis, tilted at a different angle, or even rotating in the opposite direction to the main flow. That is the bewildering reality at the center of this supergiant. These are not mere clumps of stars, they are the fossilized hearts of galaxies that were swallowed whole, the undigested nuclei of ancient cosmic victims that have retained their unique rotational identities for billions of years. The survival of these separate cores is a direct challenge to our intuition about how mergers work. When a small galaxy is consumed by a larger one, we might expect its stars to be completely assimilated, their individual motions churned into the homogeneous mix of the victor. But gravity operates with a subtlety that allows for pockets of order to persist within the chaos. Each of these decoupled cores is the remnant central bulge of a galaxy that was once independent. When its host galaxy was torn apart by tidal forces, the dense, tightly bound nucleus where the gravitational pull is strongest proved remarkably resilient. Rather than being instantly dissolved, these nuclei survived the merger relatively intact, carrying with them the momentum and rotational direction they possessed at the moment of their capture. They now orbit within the belly of the beast like swallowed diamonds that have refused to be ground down. The first of these cores, the one we've designated as the prograde core, rotates in the same general direction as the main body of NGC 4889. This suggests that the galaxy it came from was likely a satellite that had been orbiting the giant for a long time, its path gradually decaying until it was finally pulled in. Its motion is like a gear that meshes roughly with a larger gear, creating a zone of complex shearing forces where the two rotating systems meet. The second core, the retrograde core, is the true rebel. It spins in the direct opposite direction to the galaxy's primary rotation. This core is the signature of a dramatic head-on collision, a galaxy that approached from a radically different angle, perhaps even from a polar orbit. Its counter-rotation sets up a tremendous amount of dynamical friction, a gravitational drag that constantly saps energy from both systems as their stellar populations interpenetrate. The third core is perhaps the strangest, rotating on an axis that is tilted almost perpendicular to the main galactic plane. This indicates a merger that happened at a steep, oblique angle, leaving behind a nucleus that tumbles through the center of the galaxy like a wheel rolling on its side. The fact that these distinct rotational signatures have not been erased over the eons is a testament to the incredible stability of stellar orbits. The stars within each core are so densely packed and so tightly bound to each other that the gentle gravitational pulls from the surrounding stars in the main galaxy are not enough to randomize their motion completely. It's a cosmic demonstration of inertia on a grand scale. An object in motion tends to stay in motion. The galaxy has not had enough time, even across billions of years, to fully homogenize these captured nuclei. Their continued existence provides us with a frozen record of the geometry of past mergers, allowing us to reconstruct not just the fact that NGC 4889 consumed other galaxies, but the precise angles and directions from which those collisions occurred. This complex dance of opposing spins and tilted axes does more than just tell a history. It actively shapes the present-day dynamics of the galactic core. The interfaces between these decoupled cores and the main body of the galaxy are regions of intense gravitational stress. Stars passing from one rotating system to another have their paths violently altered, kicked onto new, chaotic orbits that contribute to the high-velocity dispersion we observe. This internal dynamical friction also acts as a cosmic brake, slowly converting the ordered rotational energy of the cores into random motion, which has the effect of puffing up the very center of the galaxy over time. The presence of these cores, therefore, is not a passive relic. It is an ongoing engine of stellar heating, ensuring that the heart of this giant remains a turbulent and dynamically active place, a constant reminder of the violent events that built it. But the ability of this galaxy's gravity to reshape its surroundings extends far beyond the chaotic dance of its own stars, reaching across the cosmos to literally bend the fabric of reality itself. Among the most visually stunning and scientifically profound strange objects associated with NGC 4889 is not something within the galaxy, but something it creates in the empty space far beyond its own stars, a faint, almost ethereal arc of light gracefully curved like a celestial smile. This is not a physical structure, it is a mirage, a trick of gravity known as a gravitational lens arc. It is the distorted and magnified image of an entire galaxy that lies billions of light years behind NGC 4889. Its light warped and focused by the immense gravitational field of the supergiant acting as a colossal cosmic lens. This phenomenon is a spectacular confirmation of a key prediction from Einstein's theory of general relativity. The theory tells us that mass warps the fabric of space-time, and light, traveling in a straight line through this warped space, will appear to bend from our perspective. A massive object like a galaxy can act like a lens, bending the light from objects behind it. In a perfect scenario where the lensing galaxy is a perfectly smooth and symmetrical sphere of mass, the background galaxy's light would be warped into a complete circle known as an Einstein ring. It's a concept of breathtaking elegance where the universe itself provides the tools to see the otherwise invisible. The arc we see around NGC 4889, however, is not a perfect ring. This imperfection is where the true mystery lies, transforming the arc from a mere curiosity into a precision scientific instrument. The fact that the arc is broken and asymmetrical tells us that the gravitational lens, the combined mass of NGC 4889, is not perfectly smooth. If the galaxy's mass were distributed in a simple spherical halo, we would see a much more uniform distortion. The kinks and irregularities in the arc are like fingerprints left on the lens of a telescope. They reveal the exact shape and texture of the thing doing the distorting. In this case, the distortions point directly to the invisible scaffolding of dark matter that holds the galaxy together. The arc is effectively a map, a contour lines drawn in light, tracing the otherwise hidden distribution of mass within and around the galactic titan. By meticulously analyzing the exact shape, brightness, and position of this gravitationally lensed arc, astronomers can perform a kind of cosmic tomography. They can create a highly detailed model of the total mass distribution required to produce the specific distortion they observe. This allows them to weigh the dark matter halo with incredible precision and, more importantly, to probe its structure. The irregularities suggest that the halo is not the smooth, featureless cloud that simple models often predict. Instead, it likely contains lumps and subhalos, smaller clumps of dark matter that survived the galaxy's violent assembly process. These dense knots of invisible mass exert their own tiny gravitational pulls, subtly perturbing the path of the background light and introducing the slight warps and twists we see in the arc. This makes the lens arc one of our most powerful tools for understanding the fundamental nature of dark matter itself, as different theoretical models predict different levels of substructure within these vast halos. The background galaxy whose light is being bent is itself a fascinating object, albeit one we can only see through this gravitational telescope. Due to the lensing effect, its image is not only distorted but also magnified and brightened. This cosmic magnification allows us to study a galaxy that would otherwise be far too faint and distant for our telescopes to see in any detail. We can analyze its star-forming regions, its structure, and its chemical composition at a time when the universe was much younger. The lens arc, therefore, serves a dual purpose. It illuminates the dark matter structure of a nearby giant while simultaneously providing a magnifying glass to peer into the deep, early universe. It's a single observation that unlocks secrets across billions of years of cosmic history, a perfect example of how the strangest objects often provide the most profound insights. Far out on the very fringes of NGC 4889's immense gravitational domain, well beyond its last shimmering shells of stars, lies an object that is completely invisible to optical telescopes. It is a colossal, ghostly structure that reveals itself only through the faint whisper of radio waves, a vast and diffuse cloud of emission known as a radio relic. This isn't a solid body but a cosmic afterglow, a fossilized echo of one of the most violent events ever to shake the Coma Cluster. Stretching for hundreds of thousands of light years, this relic is the celestial equivalent of a blast scar, marking the place where a titanic shock wave, traveling at millions of kilometers per hour, slammed into the thin plasma that fills the space between galaxies. Its very existence points to a cataclysm of almost unimaginable power that occurred in the distant past, a dramatic chapter in the life of this supergiant galaxy that we can only reconstruct from its lingering signature. The leading theory for the creation of such a structure involves the ghost of the central black hole's active past. Billions of years ago, when the supermassive black hole at the heart of NGC 4889 was a brilliant feeding quasar, it didn't just emit light, it generated powerful bipolar jets of relativistic particles. These jets, moving at a significant fraction of the speed of light, would have plowed outwards through the galaxy and into the intracluster medium. When such a jet eventually stalls and dissipates, its energy doesn't just vanish. Instead, it can trigger a massive shock wave that continues to propagate outwards like a tsunami traveling across an ocean. This shock wave, expanding for eons, would accelerate electrons to nearly the speed of light. When these ultra-fast electrons spiral through the weak magnetic fields that are thought to permeate the cluster, they emit synchrotron radiation, which we detect as the faint radio glow of the relic. In this scenario, the relic is the final, fading testament to the quasar's prime, a monumental shock front that has been traveling through the cosmos long after the engine that created it fell silent. However, there is another equally compelling possibility that ties back to the galaxy's violent merger history. The immense gravitational energy released during the head-on collision of two large galaxies is more than enough to generate gargantuan shock waves. Imagine the merger event that created the vast shell structures we discussed earlier. The gravitational turbulence from such a colossal impact would send powerful ripples through the intracluster gas. These merger-induced shocks could be just as effective at accelerating particles and creating the diffuse radio emission we observe. The relic's position on the outskirts of the galaxy could then be a clue to the geometry of that ancient collision, marking the furthest reach of the gravitational disturbance. Determining which of these events, the quasar outburst or the major merger, is the true culprit is one of the key challenges in understanding this object's origin story. The true power of the radio relic, however, lies not just in its existence, but in the detailed story told by its spectrum. By analyzing the exact brightness of the radio waves at different frequencies, astronomers can perform a kind of cosmic archaeology. The spectral index, which measures how quickly the radio emission fades as we look at higher and higher frequencies, acts as a clock. Over time, the accelerated electrons lose energy and the radio emission at higher frequencies fades first. A steeper spectral index, meaning the emission drops off very rapidly at higher frequencies, indicates an older population of electrons that have not been recently re-energized. This suggests the shock wave that created them happened a long time ago. A flatter spectrum, in contrast, points to a more recent injection of energy, with fresh, high-energy electrons still radiating strongly. For the relic associated with NGC 4889, the spectrum tells a story of great age. The steep spectral index reveals that this is an ancient structure, its shock wave having traveled for perhaps billions of years. The electrons have been slowly cooling, their energy dissipating into the void. This supports the idea that the relic is a fossil from a much earlier, more active era in the galaxy's life. Furthermore, the sheer size and faintness of the relic allow scientists to map the distribution of the magnetic fields within the cluster. The fact that the emission is so diffuse and structured tells us that these fields are not uniform. They are tangled and stretched by the motions of the gas, and the relic illuminates their invisible lines of force. This faint radio whisper, therefore, is far more than a cosmic curiosity. It is a dynamic probe that allows us to reconstruct the timing, power, and aftermath of cataclysmic events that shaped the entire cluster environment, giving us a unique window into the most energetic processes that can occur in the universe. Yet another clue to the galaxy's violent assembly is written in the very chemistry of its stars. a subtle but unmistakable signature that reveals a dramatic difference between its core and its outskirts. If you could take a giant cosmic spectrometer and analyze the light from stars in the very center of NGC 4889, you would find them to be remarkably metal-rich. In astronomy, metals refer to any element heavier than hydrogen and helium, the forged in the fire elements created in the hearts of stars and scattered by their explosive deaths. A high metallicity indicates a region that has experienced multiple generations of star formation and supernova, efficiently enriching the gas with these heavier elements. This rich inner core suggests a history of rapid, intense, and early star birth, a glorious burst of creation that quickly built up a dense, chemically mature stellar population. But if you then point that same imaginary instrument toward the galaxy's outermost halo, the results are startlingly different. The stars there are significantly more metal-poor, their composition much closer to the pristine hydrogen and helium that filled the early universe. This dramatic change in chemical abundance from the center to the edge is what astronomers call a steep metallicity gradient. It's as if the galaxy has a rich, complex inner city that has been recycling its materials for eons, surrounded by sprawling, underdeveloped suburbs that are still composed of largely unprocessed primitive matter. For a classic elliptical galaxy like this one, which was long thought to have formed in a single, monolithic collapse, such a sharp gradient is profoundly strange. A simple, rapid collapse would have thoroughly mixed the galactic gas, resulting in a much more uniform chemical composition throughout. The steep gradient we observe is a clear sign that the galaxy's formation was anything but simple. This chemical dichotomy points directly to a two-stage formation process, a story of two distinct eras in the galaxy's life. The first chapter was one of rapid in situ formation. Billions of years ago, a vast cloud of primordial gas, drawn into the deepest part of what would become the Coma Cluster's gravitational well, collapsed with incredible speed. In this dense central region, the first generations of massive stars ignited, lived their short, furious lives, and died in spectacular supernova, seeding the surrounding gas with the first heavy elements. This newly enriched gas then quickly collapsed to form a second, even more metal-rich generation of stars. This cycle repeated itself in a ferocious burst of activity, building the galaxy's dense core in a relatively short period of cosmic time. The inner stars, therefore, are the descendants of this efficient, self-enriching factory, bearing the chemical imprint of that frantic early period. The second chapter, which built the galaxy's outer halo, was a much slower, more violent, and fundamentally different process, accretion. After the initial core was in place, NGC 4889 began its long campaign of galactic cannibalism, consuming dozens of smaller dwarf galaxies. These satellite galaxies were themselves often metal-poor relics from the early universe, having never experienced the intense, rapid star formation needed to create a wealth of heavy elements. As these pristine systems were torn apart and their stars added to the outer halo, they diluted the galaxy's overall chemical makeup. The stars in the halo are not the products of the giant's own internal star formation. They are immigrants captured from smaller, less evolved systems. Their low metallicity is a direct reflection of their humble origins, preserving the primitive conditions of the cosmic environments where they were born. The steepness of the gradient is therefore a direct measure of the efficiency of this two-tiered history. The fact that the metal-rich core and the metal-poor halo remain so chemically distinct, even after billions of years, tells us that there has been very little mixing between these two populations. Stars formed in the inner rapid collapse have largely stayed there, on orbits that keep them confined to the central regions. Meanwhile, the stars accreted from devoured galaxies were deposited on wide, looping orbits that define the outer halo. The gravitational dynamics of the galaxy have acted to preserve this chemical segregation, allowing us to read its history like the rings of a tree. This makes the metallicity gradient one of the most powerful forensic tools available to astronomers, a silent testimony to the fact that the largest galaxies in the universe were not born in their present form, but were painstakingly assembled over time from pieces with dramatically different origins. Stretching away from the immense glow of NGC 4889 is a celestial river of incredible length and faintness, a structure that captures a cosmic crime in its very act of unfolding. This is a tidal tail, a vast and graceful arc of stars that represents the final, desperate signature of a smaller galaxy currently being dismantled by the supergiant's overwhelming gravity. Unlike the ghostly stellar streams we discussed earlier, which are the cold, faded remnants of mergers long since completed, this tail is a snapshot of destruction in real time, or rather, in the slow, grand time of the universe. It is the galactic equivalent of seeing a comet's tail, a trail of debris pointing directly back to the victim being consumed. The process creating this breathtaking sight is tidal disruption, a subtle but relentless force of nature. It begins when a smaller galaxy ventures too close to the immense gravitational well of NGC 4889. The key to understanding this destruction lies in the difference in gravity's pull. The side of the small galaxy facing the giant experiences a much stronger gravitational tug than the side facing away. This difference, the tidal force, acts like a cosmic stretching machine. It doesn't smash the galaxy like a hammer, it patiently pulls it apart like taffy. The galaxy is stretched along the line pointing toward the giant and compressed from the sides. Over successive orbits, stars and gas from the outer regions of the victim are stripped away, drawn out into two long streams, one leading ahead of the galaxy and one trailing behind. The stream we see is this trailing tail, a ribbon of stars being flung outwards as the galaxy swings past the point of closest approach. By carefully measuring the properties of this tidal tail, astronomers can perform a kind of cosmic forensics, reconstructing the identity of the victim. The total brightness of the stream, though incredibly faint, allows for an estimate of how many stars have already been stripped away. Combined with the tail's length, which can span hundreds of thousands of light years, scientists can make an educated guess about the original mass of the devoured galaxy. The evidence suggests this was not a tiny, fragile dwarf galaxy, but likely a more substantial object, perhaps a small spiral or irregular galaxy with a total mass of several billion suns. It was a respectable island universe in its own right, now being unraveled into a cosmic thread. The fate of this galaxy is sealed, but its final assimilation will be a drawn-out affair. The process of tidal stripping is not instantaneous. It can take billions of years to complete. The galaxy's core, where the stars are most densely packed and the gravitational bonds are strongest, will hold out the longest. It will continue to orbit the giant, losing mass with each pass, gradually diminishing until it is fully dissolved into the halo of NGC 4889. The tidal tail itself will also evolve, its stars slowly dispersing and mixing with the general stellar population of the supergiant, eventually becoming indistinguishable from the other ghostly streams that testify to this galaxy's cannibalistic past. For now, this magnificent structure serves as a living laboratory, allowing us to watch a fundamental process of galactic evolution as it happens, a stark reminder that even in the apparent serenity of the cosmos, the laws of gravity are continually reshaping the universe. Now, if we shift our gaze from the visible starlight and peer into the universe using the eyes of a radio telescope, the structure of NGC 4889 transforms into something even more immense and spectacular. Extending far beyond the faint glow of its trillion stars, we find two colossal, symmetrical lobes of radio emission, like a pair of ghostly lungs straddling the galactic core. Each lobe is a vast bubble of energetic particles, stretching for hundreds of thousands of light years into the intergalactic void. These are the galaxy's double radio lobes, and they are a direct, fossilized imprint of the central black hole's most violent and energetic phase. They represent a time when this sleeping giant was a brilliant quasar, blasting its power across the cosmos. The mechanism that created these enormous structures is one of the most powerful engines in the universe. During its active phase, the supermassive black hole wasn't just passively consuming matter. It was channeling a tremendous fraction of the gravitational energy released by infalling material into two narrow, highly focused jets. These jets, composed of plasma accelerated to nearly the speed of light, shot out from the black hole's poles perpendicular to its accretion disk. They acted like cosmic blowtorches, plowing through the galaxy's own gas and then out into the much thinner intracluster medium. When these incredibly fast-moving jets finally slammed into the denser material at their leading edges, they lost their focus and ballooned outward, inflating these gigantic lobes with a hot soup of magnetic fields and relativistic particles. The entire structure acts as a colossal energy storage system, a battery charged by the black hole's past fury. What makes these particular lobes so strange, however, is not their existence but their current state of profound quiet. They are unusually faint and lack the bright, compact hotspots that we typically see at the outer edges of active radio galaxies. These hotspots are the telltale sign of an ongoing energy supply, the places where a still active jet is continuously slamming into the intergalactic medium, creating a brilliant shock front. The absence of such hotspots in NGC 4889's lobes is a clear indication that the engine has shut down. The jets have ceased, the central AGN has switched off. What we are observing now are not active lobes being constantly refueled, but fossilized remnants. The particles within them are still emitting radio waves as they spiral along magnetic field lines, but they are like the dying embers of a once roaring fire, slowly cooling and fading without a fresh supply of fuel. This leads to a fascinating cosmic detective story. By studying the properties of this fading radio light, astronomers can essentially perform carbon dating on the black hole's last major outburst. The radio emission we detect comes from electrons that were accelerated during the jet's active phase. Over millions of years, these high-energy electrons lose their energy through radiation and interactions. The spectral index of the radio waves, how their brightness changes with frequency, acts as a clock. A steeper spectral index, where the higher frequency radio waves have faded dramatically, indicates an older population of electrons that have been coasting without a fresh energy injection for a very long time. For NGC 4889, the spectral signature points to an age of several 100 million years, perhaps even longer. This means the quasar that built these immense structures likely fell silent around the time dinosaurs were becoming the dominant life forms on Earth. The lobes are a monumental echo of an era that has long since passed. The sheer size and symmetry of these fossil lobes also provide a unique way to probe the environment surrounding the galaxy. The fact that they have remained so intact and symmetrical, rather than being shredded or distorted, tells us that the intracluster medium through which they expanded must be remarkably smooth and uniform on large scales. Any significant clumpiness or turbulence in the external gas would have caused the lobes to bend, warp, or become asymmetrical. Their pristine shape is therefore a map of the calm, steady pressure of the cluster's hot plasma. Furthermore, by measuring the total energy stored in these lobes calculated from their size and the strength of their radio emission, scientists can make a direct estimate of the total amount of energy the black hole unleashed during its active phase. It's a staggering number, equivalent to the energy released by billions of supernovae, a testament to the raw power that once raged at the heart of this now quiet giant. These silent, expanding bubbles are more than just relics. They are a permanent record of the most energetic chapter in the galaxy's life, a chapter whose final words were written in radio waves across the void. But the gravitational turmoil near the galaxy's core has forged even stranger stellar societies than the blue stragglers. Tucked in dangerously close to the central supermassive black hole, astronomers have identified a population of stellar objects so extreme they defy easy classification. These are hypercompact star clusters, and they represent a true borderline case in celestial physics, pushing the definitions of what a star cluster can be. Imagine taking a globular cluster, one of those ancient, dense swarms of up to 1,000,000 stars, and then crushing it down to a fraction of its normal size while somehow making it even more massive. The result would be one of these hypercompact enigmas, an object with the mass of a small dwarf galaxy packed into a volume so small it could fit comfortably within the distance from our Sun to its nearest stellar neighbors. The properties of these clusters are nothing short of staggering. A typical globular cluster might be 100 light-years across. A hypercompact cluster crams a similar number of stars into a region only a few light-years in diameter. This incredible density means the stars within are packed together with a proximity that is almost unimaginable. If you were standing on a planet orbiting a star in the heart of one of these clusters, the night sky wouldn't be a scattering of points of light. It would be a continuous, brilliant glow, with thousands of stars appearing as bright as Venus does in our own sky. The gravitational interactions within such a tight space would be constant and violent, leading to frequent stellar collisions and the rapid formation of exotic objects like blue stragglers and X-ray binaries. This is a stellar environment operating at its absolute physical limit. The most compelling mystery is how such incredibly dense objects could form and, more importantly, survive in their current location. The region immediately surrounding a supermassive black hole is one of the most hostile places in the universe, dominated by unimaginably powerful tidal forces. Any normal star cluster that ventured too close would be shredded, its stars torn apart or scattered into the chaotic stellar population of the galactic core. The very existence of these hypercompact clusters so close to the brink suggests they must possess an internal strength, a gravitational cohesion far beyond that of a typical globular cluster. This has led to a fascinating theory. Perhaps these objects are not simply born dense, but were made dense by the black hole itself. A normal globular cluster on an elliptical orbit that passes perilously close to the black hole could have its outer layers of stars systematically stripped away by tidal forces during each close approach. What remains after billions of years of this gravitational pruning is only the cluster's incredibly dense, hard-to-disrupt core, which has been compressed even further by the ordeal. It's a form of natural selection where only the toughest, most densely packed stellar systems can survive in the black hole's deadly neighborhood. An alternative, and even more dramatic origin story proposes that these hypercompact clusters are the naked nuclei of galaxies that were completely vaporized. We've discussed how NGC 4889 cannibalizes smaller galaxies, leaving behind streams and sometimes intact cores. But for the very smallest galaxies, the tidal forces during ingestion could be so overwhelming that they are completely dismantled, with one crucial exception: their central star cluster. Many small dwarf galaxies possess an exceptionally dense cluster at their very center. If the dwarf galaxy is ripped apart, this resilient nuclear cluster might be all that remains, left orbiting the supergiant as a solitary, hypercompact testament to a galaxy that no longer exists. In this scenario, these objects are not clusters in the traditional sense, but the ghostly hearts of long-dead galactic companions. Studying these borderline objects is crucial because they could represent a missing link in our understanding of how the most massive stellar systems form. They occupy a fascinating gray area between globular clusters, which form from a single giant molecular cloud, and dwarf galaxies, which are anchored by their own dark matter halos. By measuring the motions of stars within them, astronomers are trying to answer a fundamental question: do these hypercompact clusters contain dark matter? If they do, it would strongly support the idea that they are the remnants of devoured galaxies. If they are held together solely by the gravity of their visible stars, it would point to a unique formation process involving extreme tidal compression. Their survival in the gravitational maelstrom of the galactic center makes them natural laboratories for testing the limits of stellar dynamics, offering a unique glimpse into the violent processes that shape the most extreme environments in the cosmos. This journey into the heart of NGC 4889 has revealed a galaxy built from chaos, a place where black holes dance and stellar streams weave a history of destruction. But one of the most telling clues to its violent past comes not from what is present at its center, but from what is subtly yet unmistakably misaligned. When astronomers painstakingly mapped the galaxy, they made a perplexing discovery: the peak of the ancient activity from the central supermassive black hole, the ghostly signature of where the brilliant quasar once shone, is not located at the exact photometric center of the galaxy, the point around which the trillion stars symmetrically orbit. It's offset by a small but significant distance, as if the engine of the entire galaxy has been knocked slightly off its foundation. This misalignment is a profound puzzle. In a simple, serene elliptical galaxy that formed in isolation, you would expect the most massive object, the supermassive black hole, to sit perfectly at the gravitational bottom of the well, the still point around which everything else revolves. The fact that it doesn't suggests that the galaxy's core has experienced a recent, in cosmic terms, and dramatic event that physically displaced the black hole from its equilibrium position. The leading explanation for such a kick is as elegant as it is violent: a recoil from the emission of gravitational waves during a black hole merger. To understand this, picture the final moments of two supermassive black holes spiraling together. As they whirl around each other at a significant fraction of the speed of light, they radiate away tremendous energy in the form of gravitational waves, ripples in space-time itself. If this dance is perfectly symmetrical, if the two black holes are of identical mass and their spins are perfectly aligned, the gravitational waves are emitted symmetrically, and the final, merged black hole is born at rest. But nature rarely produces such perfect symmetry. If there is any asymmetry, say in the masses or the directions of the black hole's spins, the gravitational waves will be emitted more strongly in one direction. According to the law of conservation of momentum, the final black hole must recoil in the opposite direction, like a rocket firing its engine in one direction and moving in the other. This gravitational wave kick can be powerful enough to literally punt the newly formed supermassive black hole right out of the galactic center at speeds of thousands of kilometers per second. In the case of NGC 4889, the kick may not have been strong enough to eject the black hole completely, but it could have been sufficient to displace it, sending it oscillating back and forth through the core like a clapper in a bell, with the offset we see today being a snapshot of one point in that long, slow oscillation. However, the gravitational wave kick is not the only possible culprit. The offset could also be a signature of an ongoing gravitational argument that has not yet been resolved. We've already discussed the possibility of a binary or even a triple black hole system at the galaxy's heart. If the brightest point of activity we detect is associated with one member of a binary pair, it would naturally appear offset from the system's common center of mass. As the two black holes orbit each other, the location of the most intense accretion and radiation could shift over time, depending on which black hole is actively feeding at any given moment. The dynamics here are incredibly complex. The accretion of gas onto a binary system can be highly asymmetric, with one black hole often dominating the feast due to its larger appetite or a more favorable position. What we interpret as a permanent offset might actually be a temporary state in a long-term, evolving dance, a fleeting alignment that our telescopes have captured at a particular moment in a multi-million-year cycle. This strange misalignment, therefore, is far more than a minor curiosity about galactic geometry. It serves as a direct probe of the most extreme gravitational physics imaginable. By precisely measuring the size of the offset and comparing it to sophisticated simulations of black hole mergers, Astronomers can estimate the properties of the black holes that merged, their masses and spins, and the violence of the event that created the current Leviathan. It's a way of using the present-day structure of the galaxy to witness a cataclysm that occurred billions of years in the past. Furthermore, if the offset is indeed due to an ongoing binary, monitoring it over time could, in theory, reveal the orbital motion of the black holes, providing indirect evidence for their presence and setting the stage for a future merger that would shake the very fabric of the cosmos. This slight deviation from the center is a whisper from the realm of strong gravity, a subtle clue that the heart of this sleeping giant may still harbor the echoes of a colossal collision. Among the ancient stellar population of NGC 4889, where change often unfolds over billions of years, a trio of stars presents a mystery that operates on a more human, yet still profoundly slow timescale. These are the ultra-long period variables, 3 stars that undergo enormous changes in brightness, but with a rhythm so drawn out it defies conventional explanation. While most variable stars flicker over days, weeks, or months, these objects take several years to complete a single cycle of brightening and dimming. Their variability is not a rapid pulse but a languid cosmic heartbeat, a signal so gradual that observing a complete cycle requires a level of patience that spans a significant portion of an astronomer's career. This extraordinary slowness is the core of the puzzle, as it places them outside the neatly defined categories for most known variable stars. The first possibility for their strange behavior points to the stars themselves being true leviathans, far larger than any star in our own galaxy. Imagine a supergiant star so immense that if placed at the center of our solar system, its outer atmosphere would reach beyond the orbit of Jupiter. These hypergiants are inherently unstable, balancing on a precarious edge where their own immense gravity struggles to hold their bloated atmospheres together. They undergo slow, convulsive pulsations, expanding and contracting over periods of years. As they swell, their surface cools, and they may also eject huge clouds of dust. This dust, condensing in the cooler outer layers, can temporarily obscure the star's light, causing a very gradual dimming. When the star eventually contracts and heats up again, the dust dissipates or is blown away, and the star brightens once more. In this scenario, the ultra-long period is simply a reflection of the slow, ponderous oscillations of a stellar behemoth in its final stages of life. A second, more interactive theory involves not one star but 2, locked in a symbiotic relationship with a remarkably wide separation. A symbiotic star system typically consists of a red giant and a small, hot white dwarf. The red giant steadily loses its outer atmosphere in a slow stellar wind, and the white dwarf gathers this material onto its surface. In most known symbiotic stars, the orbital period is measured in years, leading to regular outbursts. However, for the trio in NGC 4889, the orbital period could be vastly longer, perhaps lasting decades. The variability we see might not be from a full orbit, but from unpredictable episodes of mass transfer. A clump of material from the giant could fall onto the white dwarf, triggering a temporary flare, or the accumulation of gas on the white dwarf's surface could reach a critical density and ignite in a slow, controlled thermonuclear explosion, causing a years-long brightening. The long period would then be a signature of an incredibly wide binary system where interactions are rare, dramatic, and drawn-out events. Perhaps the most exotic possibility is that we are witnessing the gradual eclipse of a star by a circumstellar disk of phenomenal scale. Consider a binary system where one star is surrounded by a vast, thick disk of gas and dust, like a gigantic version of Saturn's rings but on a stellar scale. If our line of sight is nearly edge onto this disk, the companion star would take years to pass behind it, experiencing a very slow and steady dimming as it is occulted by the disk's outer material. The exact shape of the dimming curve, how smoothly and symmetrically the light fades and returns, could reveal the structure and density of the disk itself. This would make the ultra-long period variable not just a star, but a signpost for a rare and massive planetary system in formation, or the aftermath of a catastrophic collision between planets around one of the stars. Distinguishing between these theories is a monumental challenge due to the sheer timescale involved. A single observation tells you very little. You need a light curve, a graph of brightness over time, that spans decades to even begin to understand the pattern. This requires a legacy of observations, combining data from old photographic plates with modern digital measurements, a project that truly tests the endurance of scientific inquiry. Each slight flicker in brightness, each change in color, becomes a precious data point in a puzzle that may take a human lifetime to solve. These three strange stars, with their patient, rhythmic changes, remind us that the universe operates on timescales far beyond our own, and that some of its most profound mysteries reveal themselves not in a flash but in the slow, relentless passage of time. Now, if we peer into the very center of NGC 4889, not with the broad brush of a camera, but with the precise scalpel of a spectrometer, we find a spectroscopic signature that is both common and deeply puzzling. The nucleus of this supergiant galaxy is classified as what astronomers call a low-ionization nuclear emission region, or a LINER for short. This somewhat clunky name describes a very specific set of faint emission lines in the galaxy's spectrum, a fingerprint indicating that the gas in its core is in a peculiar state. It's hot enough to glow, but only just barely. It's not the brilliant, high-energy emission of a full-blown quasar, nor is it the complete silence of a truly dead core. Instead, it's a faint, persistent whisper of activity, a low-energy simmer that has sparked a major debate about what exactly is keeping the galactic hearth warm. The central question is one of energy sources. What physical process is providing just enough power to make this gas softly glow without triggering the brilliant outburst of a younger galaxy? The traditional and most straightforward explanation points back to the supermassive black hole, but in a much diminished role. This theory suggests we are seeing a low-luminosity active galactic nucleus, an AGN that is running on fumes. Imagine the black hole is not entirely dormant. It might be slowly accreting a tenuous trickle of gas, perhaps from the stellar winds of the countless old stars that swarm around it. This meager fuel supply would generate a faint, hot accretion disk, producing just enough ultraviolet radiation to weakly ionize the surrounding gas, creating the specific LINER emission lines we observe. It would be the astrophysical equivalent of a pilot light on a massive furnace, a tiny flame indicating the system is still connected to its fuel source, even if it isn't roaring to life. However, a compelling alternative theory argues that the black hole might not be involved at all. The core of NGC 4889 is packed with ancient, evolved stars, specifically a large population of hot, post-asymptotic giant branch stars. These are sun-like stars in a very late and brief phase of their evolution, where they emit a significant amount of soft ultraviolet radiation. If enough of these stars are concentrated in the nucleus, their collective ultraviolet output could be sufficient to power the LINER emission. In this scenario, the glow isn't coming from a central monster, but from a retirement community of stars, each in its final energetic throes, whose combined light provides the gentle ionization. This would make the LINER not a sign of AGN activity, but a natural symptom of a very old, very dense stellar population. A third possibility introduces a more violent, mechanical source of energy, shock waves. The galactic center is a tumultuous place with stellar winds from countless stars constantly colliding. Furthermore, the random, high-velocity orbits of stars themselves create sonic booms as they move through the diffuse interstellar gas. These collisions and booms generate powerful shock waves that can heat the gas to temperatures high enough to produce the observed emission lines, all without needing any significant radiation from either a black hole or hot stars. It would be a purely kinetic form of heating, like the glow from a meteor heated by its passage through the atmosphere, but on a galactic scale. The reason this debate is so important is that liner are incredibly common, especially in massive elliptical galaxies like this one. Understanding what powers them is essentially about understanding the final, long-term state of galactic nuclei. Is the faint glow a sure sign of a barely active black hole, implying that even the quietest giants still have a heartbeat? Or is it the natural signature of a galaxy that has truly moved beyond its active phase, its core now illuminated only by the gentle light of its dying stellar citizens? By studying the precise details of the liner in NGC 4889, such as the exact ratios of different emission lines and the spatial extent of the glowing gas, astronomers hope to crack this code. This faint spectroscopic whisper, therefore, is more than just a classification. It is a key diagnostic tool, its subtle nuances holding the answer to how the most massive galaxies in the universe spend their cosmic retirement. But the story of this supergiant galaxy extends far beyond its own clearly defined borders into the seemingly empty space that surrounds it. If you were to take a long exposure image of the entire Coma Cluster and then meticulously subtract the light from every single galaxy, including the brilliant core of NGC 4889, you would not be left with perfect blackness. Instead, a faint, ghostly glow would remain, a pervasive light that fills the spaces between the galaxies like a cosmic fog. This is the intracluster light, and a significant portion of this ethereal illumination can be traced directly back to the gravitational violence orchestrated by our galactic titan. It represents a vast population of stars that have been utterly liberated from their home galaxies, condemned to wander the intergalactic void forever, and their collective glow provides a unique window into the cluster's turbulent past. The primary engine for creating this phantom starlight is the same process we've seen evidence of again and again: tidal stripping. As galaxies like NGC 4889 swing past their smaller neighbors, or as smaller galaxies plunge through the dense core of the cluster, their gravitational interactions are relentless. The tidal forces that pull galaxies apart to form the distinct streams and tails we can resolve are also constantly at work on a more subtle, continuous scale. With each close encounter, stars are gently but persistently nudged from the outer halos of their host galaxies. Unlike the dramatic, coherent streams that mark a recent major disruption, these stars are scattered in all directions, their orbits randomized by the complex gravitational field of the entire cluster. Over billions of years, this steady trickle of stellar escapees has built up into a diffuse sea of stars, a cosmic diaspora that belongs not to any one galaxy, but to the cluster as a whole. Given its immense mass and central location, NGC 4889 is the dominant contributor to this process, its gravitational influence serving as the primary factory for intracluster stars. Studying this incredibly faint glow is one of the most formidable challenges in observational astronomy. The surface brightness of the intracluster light is often hundreds of times dimmer than the natural glow of our own night sky, requiring exceptionally dark observing sights and sophisticated image processing techniques to detect. But the scientific payoff is immense because this light acts as a direct tracer of the cluster's total gravitational potential. The stars that make up the intracluster light are in effect test particles moving freely within the cluster's gravity well. By mapping the detailed distribution and density of this faint glow, astronomers can create a three-dimensional map of the cluster's dark matter distribution. The intracluster light settles into the gravitational contours of the cluster, much like flour dusted over a vibrating drumhead reveals the pattern of the vibrations. It outlines the unseen structure that governs the motion of everything within it. Furthermore, the intracluster light is a fossil record of the cluster's merger history. The specific patterns within the glow can reveal ancient events that are no longer visible in the current arrangement of galaxies. For instance, a smooth and symmetrical distribution of intracluster light suggests a long, gradual buildup over the cluster's lifetime. through the slow and steady stripping of many galaxies. However, if the glow is clumpy or shows large-scale asymmetries, it could be the signature of a relatively recent massive merger between two large subclusters. The stars stripped during such a colossal event would retain a memory of the collision, their distribution pointing back to the direction and dynamics of the impact. In this way, the faint, diffuse light that might be dismissed as background noise is actually a rich archive, preserving the memory of the most violent events in the cluster's life. It allows us to see not just the current state of the cosmos, but the echoes of the collisions and interactions that shaped it over billions of years. But after all this focus on the internal dynamics and the relics orbiting this supergiant, it's easy to forget a fundamental fact. NGC 4889 is not a stationary object. It is a colossal ship sailing through the cosmic ocean of the Coma Cluster at a breathtaking speed of millions of kilometers per hour. For a long time, astronomers assumed its motion was a simple, predictable arc around the cluster's center of mass, a stately dance governed by the smooth, cumulative gravity of thousands of galaxies. However, when advanced telescopes like the Hubble Space Telescope made exquisitely precise measurements of its proper motion, its tiny, actual shift in position against the backdrop of more distant galaxies over a period of years, they revealed something subtle yet significant. The galaxy is moving in a slightly unexpected way, its path deviating from the predicted course. This anomaly, this strange proper motion, is a tiny wiggle in the trajectory of a trillion sun giant, and it whispers secrets about the invisible architecture of the entire cluster. To understand why this slight deviation is so telling, imagine you're driving a car on a long, straight highway that you believe is perfectly smooth. If the car suddenly veers ever so slightly to one side, you would suspect a cause. Perhaps a strong crosswind, or maybe the road itself has an unseen camber or a dip. For NGC 4889, the road is the gravitational landscape of the Coma Cluster, a landscape that, according to our best models, should be shaped primarily by the smooth distribution of dark matter. The fact that the galaxy's motion doesn't perfectly match this model means the road is not as smooth as we thought. The most compelling explanation is that the dark matter halo of the Coma Cluster is not the simple, symmetrical cloud we often depict. Instead, it must be lumpy, containing dense, invisible clumps or subhalos of dark matter associated with individual galaxies. As NGC 4889 moves, the gravitational pull from one of these unseen dark matter clumps could be subtly tugging it off its expected path, like a ship being pulled by a hidden underwater current. This possibility leads to a fascinating detective story. By analyzing the exact nature of the deviation, its direction and magnitude, astronomers can work backwards to map these invisible masses. It's a technique called gravitational dynamics, where the motion of a visible object is used to infer the presence and location of an invisible one. If the peculiar motion suggests the galaxy is being pulled towards a specific region of seemingly empty space, that region likely contains a significant concentration of dark matter, perhaps from a galaxy that is too faint for us to see or that has been mostly stripped away, leaving only its dark matter skeleton behind. This makes the strange proper motion of NGC 4889 a powerful probe, its trajectory acting like a compass needle pointing toward the hidden mass concentrations that dominate the cluster's gravity. However, there is another, equally dramatic possibility that could explain the anomalous motion. What if this deviation is not the result of a static lump of dark matter, but the lingering gravitational echo of a recent close encounter? The Coma Cluster is a crowded place, and while direct collisions between giant galaxies are rare, near misses are not. It's possible that within the last billion years, NGC 4889 had a gravitational dance with another massive galaxy, one that passed just close enough to give it a significant gravitational slingshot. Such an interaction wouldn't have to result in a merger. the two galaxies could have swung past each other, their mutual gravity altering each other's velocity in a lasting way. The observed proper motion could be the galaxy's new trajectory, set by that ancient encounter, a change in course that has persisted long after the other galaxy has receded into the distance. This scenario turns the galaxy's motion into a cosmic fossil record of a specific event. By running sophisticated computer simulations that recreate the gravitational dynamics of the cluster, scientists can test whether introducing a close passage with a galaxy of a certain mass and at a certain time in the past can reproduce the exact proper motion we observe today. If they find a match, it wouldn't just solve the mystery of the motion. It would also give us a precise history of a major dynamical event in the cluster, telling us which galaxy was the interaction partner and when it happened. This would add another layer to our understanding of how the most massive galaxies in the universe jostle for position, their paths shaped by brief but powerful gravitational handshakes that can redirect their journeys for eons. Whether the cause is a hidden clump of dark matter or the ghost of a past encounter, the slight unexpected drift of this galactic titan proves that even the largest structures are subject to the invisible tugs and pushes of their environment, their motions writing a hidden history on the cosmos. And now we turn our attention to a concept so radical it challenges the very definition of a galaxy. In the gravitational shadow of NGC 4889, astronomers have pinpointed two regions of profound emptiness that are, paradoxically, among the heaviest objects we have yet encountered. These are not voids, but gravitational anchors, areas where the fabric of space-time is curved so strongly that they create unmistakable lensing effects on the light from background galaxies. Yet when we point every telescope we have at these spots, we see absolutely nothing. No stars, no gas, not even a faint smudge of dust. They are, for all intents and purposes, completely dark. These enigmatic spots are our leading candidates for what could be true dark galaxies, and if confirmed, they would represent a form of cosmic life that failed to ignite. Imagine a galaxy that never was. According to our prevailing theories of cosmic structure, the first thing to form in the early universe was not stars, but vast webs of dark matter. Gravity would have pulled this invisible substance into clumps and halos, and these halos would then have acted as gravitational wells, drawing in the normal hydrogen gas from which the first stars would eventually be born. But what if, in some cases, that next step never happened? A dark galaxy candidate is precisely that, a massive halo of dark matter that, for some unknown reason, never managed to pull in enough gas, or the gas it did attract was prevented from cooling and collapsing into stars. It would be a galaxy that skipped its primary purpose, a cosmic structure with all the mass and gravity of a true galaxy, but forever cloaked in darkness, a skeleton without flesh. The evidence for these two candidates comes entirely from the subtle art of gravitational lensing. As light from incredibly distant quasars travels toward us, it passes through the gravitational field of the Coma Cluster. In these two specific locations, that light is bent and distorted in a way that indicates a significant concentration of mass. By mapping the precise warping of the background galaxy's shapes, astronomers can calculate the mass of the object causing the lensing. The results are staggering. Each of these nothings appears to possess the mass of a small dwarf galaxy, perhaps tens of billions of times the mass of our Sun. The sheer power required to bend light so noticeably must come from somewhere, and the complete absence of any visible source makes the case for dark matter overwhelming. It's like feeling a powerful gust of wind on a perfectly still day, an invisible force whose presence is undeniable even though you cannot see its source. Confirming the existence of a true dark galaxy, however, is a monumental challenge. The primary hurdle is the very thing that defines them, their darkness. How do you prove an object exists when it emits no light for our telescopes to capture? the main strategy involves searching for the faintest possible traces of normal matter that might still be associated with the dark halo. Astronomers use ultra-sensitive radio telescopes to scan for the signature of cold hydrogen gas, the raw material for stars. Even if a dark galaxy failed to form stars, it might still hold onto a reservoir of this primordial gas. Detecting a faint cloud of hydrogen that coincides perfectly with the gravitational lensing signal would be the next best thing to a direct confirmation, providing the smoking gun that a dark matter halo is indeed present and has some atomic matter associated with it. Another possibility is that these objects are not pristine dark galaxies, but the ghosts of galaxies that were strangled at birth. Perhaps they did form a small population of stars long ago, but were then rapidly stripped of their gas by the harsh environment of the Coma Cluster. The intracluster medium, that searing wind we've discussed, could have scoured them clean before they could develop into a bright, recognizable dwarf galaxy. What would remain is a cluster of old, dim stars that is simply too faint for our current telescopes to detect at such a great distance. In this scenario, the object wouldn't be a true dark galaxy, but a failed or stripped galaxy, its stellar population so feeble and diffuse that it blends into the faint intracluster light. Distinguishing between a genuinely starless dark galaxy and an extremely faint, star-poor one is one of the toughest observational challenges in modern extragalactic astronomy. The implications of confirming a genuine dark galaxy would ripple through our understanding of cosmic evolution. Their existence would provide crucial support for the theory that dark matter halos are the true scaffolding of the universe, and that the bright galaxies we see are just the lucky ones that successfully turned their gas into stars. It would also help solve a long-standing puzzle in cosmology, the missing dwarf galaxy problem. Computer simulations of dark matter predict that large galaxies like the Milky Way should be surrounded by hundreds, even thousands, of small dark matter halos. Yet we only see a few dozen small satellite galaxies. Where are the rest? The answer could be that the vast majority of these small halos are, in fact, dark galaxies, invisible halos that never lit up. The two candidates near NGC 4889 could be the tip of a vast iceberg, representing a hidden population of dark structures that far outnumber the bright galaxies we see, a silent majority that has shaped the cosmos from the shadows. But to truly understand the scale of this cosmic cannibal, we must learn to read the light of its ancient stars not as a single story, but as a layered history book. Every star in NGC 4889 has a chemical fingerprint, a specific blend of elements forged in the heart of the star that birthed it. By dissecting the galaxy's overall light with a spectrometer, astronomers can perform a kind of cosmic archaeology, separating the contributions of different generations of stars. And what this analysis reveals is astonishing. The light of this apparently serene, red giant carries the unmistakable signature of not one, but several distinct and incredibly violent periods of star formation in its deep past. It is not the product of a slow, steady build-up, but of a series of colossal starbursts, frenzied epochs where star birth occurred at a rate hundreds or even thousands of times greater than what we see in our own Milky Way today. The trigger for these ancient firestorms was almost certainly the same process that built the galaxy's immense size, galactic mergers. Imagine the scene billions of years ago when two large, gas-rich galaxies were drawn together by gravity. As they collided, their vast clouds of hydrogen gas did not simply pass through one another. Instead, they experienced immense shock waves and turbulent pressures, compressing the gas to unprecedented densities. This was the perfect recipe for a starburst. In these compressed regions, gravity could take hold far more efficiently, causing thousands of stellar nurseries to ignite almost simultaneously. The galaxy would have transformed into a brilliant blue-white beacon, blazing with the light of millions of newborn massive stars. These stars, however, were destined for short, spectacular lives, burning through their fuel in only a few million years before exploding as supernova. Each of these supernovae was a cosmic forge, blasting space with newly created heavy elements, the carbon, oxygen, iron, and silicon that are the building blocks of planets and life. In a starburst, these explosions come in such rapid succession that they create a continuous wave of enrichment, seeding the surrounding gas with these metals. The next generation of stars to form from this enriched gas would therefore contain a higher metallicity. By finding distinct groups of stars within NGC 4889 that have different specific metallicities, astronomers can identify the separate starburst events. It's like finding distinct layers of sediment in a geological core sample. Each layer represents a different cataclysmic period of construction. The galaxy we see today is the final product, a cumulative record of these successive bursts, with the stars from each merger and starburst event now thoroughly mixed together through billions of years of orbital motion. This fossil record of starbursts solves a key paradox about supergiant elliptical galaxies. Their current quiescent state suggests a long, quiet retirement, but their immense mass and complex structure demand a violent, explosive youth. The evidence hidden in their starlight confirms the latter. The starbursts were not just dramatic side effects of mergers, they were the primary mechanism by which the galaxy converted its acquired gas into stars with ruthless efficiency. This rapid, bursty mode of star formation is fundamentally different from the gradual, sustained process we see in spiral galaxies. It's the difference between a sudden, raging wildfire and a carefully managed campfire. The starbursts allowed NGC 4889 to build its colossal stellar population in a relatively short period of cosmic time, a series of glorious, violent growth spurts that shaped the giant we observe in the present day. Now, if we shift our perspective from the grand choreography of stars and dark matter to a more subtle, invisible force, we encounter a strange object that permeates the very space between the stars, the galaxy's anomalous magnetic field. We often picture elliptical galaxies as simple, serene swarms of stars, largely devoid of the complex structures found in their spiral cousins. This includes magnetic fields, which in spiral galaxies are typically ordered along the majestic arms, generated and maintained by the constant churning of gas and ongoing star formation. But when astronomers trained their radio telescopes on NGC 4889 to measure its magnetic field, they discovered something that defies this quiet expectation. The field is not weak and chaotic. It is surprisingly strong and exhibits a large-scale, ordered structure, a finding that challenges our basic understanding of what an old, gas-poor galaxy should be like. The origin of this powerful and organized magnetic field is a fascinating puzzle. One compelling theory points directly to the galaxy's explosive past, specifically to the era when its central black hole was a brilliant quasar. During that hyperactive phase, the jets blasting from the black hole would have been filled with magnetized plasma. As these jets plowed outwards for hundreds of thousands of light years, they could have effectively injected a coherent magnetic field into the vast volume of the galaxy's halo, imprinting it with a large-scale order. Even after the jets shut down and the lobes began to fade, the magnetic field they left behind could have persisted, frozen into the tenuous gas that permeates the galaxy. It's like a cosmic branding iron, leaving a permanent mark that lasts long after the fire has gone out. The field we measure today could be the fossilized remnant of that ancient, colossal energy output. An alternative, or perhaps complementary, explanation involves the galaxy's violent merger history. When two galaxies collide, their interstellar mediums, including their magnetic fields, become violently entangled. This chaotic process might seem like it would create a tangled mess, but under the right conditions, it can actually amplify and organize the field. The immense turbulent motions during a major merger can act like a cosmic dynamo, stretching and twisting the magnetic field lines, thereby strengthening them. Furthermore, if the merging galaxies had their own ordered fields, the merger could have brought them together in a way that, after the turmoil subsided, resulted in a new, large-scale coherent field for the combined galaxy. The strong magnetic field in NGC 4889 could therefore be a legacy of its cannibalistic nature, a signature of the tremendous forces unleashed when galaxies smash together. This magnetic field is far from being a passive relic. It plays an active and crucial role in shaping the galaxy's present-day environment. One of its most important functions is confining the hot gas that we know exists within the galaxy. Even though NGC 4889 is largely gas-poor, its interior is not a perfect vacuum. It contains a halo of very hot, diffuse plasma. The magnetic field, with its lines of force weaving through this gas, acts like an invisible cage. It provides pressure that helps prevent this hot gas from simply dissipating into the even hotter intracluster medium, effectively trapping it within the galaxy's gravitational domain. This confinement influences the energy balance of the galaxy, affecting how heat is distributed and potentially playing a role in the very long-term cooling of this material. Furthermore, this magnetic field is a master conductor for cosmic rays. These high-energy particles, primarily protons and electrons accelerated by supernova remnants or the central black hole in the past, travel through the galaxy at nearly the speed of light. But they don't travel in straight lines. The magnetic field forces them to spiral along its lines of force, guiding their paths and preventing them from escaping too quickly. This has the effect of filling the galaxy with a persistent fog of cosmic ray energy, which adds another form of pressure to the interstellar medium. The presence of a strong, ordered field means that these cosmic rays can be channeled more efficiently, potentially influencing regions far from their sources and contributing to the overall pressure support that keeps the hot gas from collapsing. The anomalous magnetic field of NGC 4889, therefore, is not just a curious artifact. It is a dynamic component of the galaxy's ecosystem, a hidden force that continues to govern the behavior of matter and energy within this cosmic giant. Surrounding the immense galaxy like a cloud of ancient fireflies, the thousands of globular clusters orbiting NGC 4889 present a spectacle of their own. Each of these dense spherical swarms, containing up to 1 million stars, is a fossil from the earliest epochs of the universe. For astronomers, the collective population of these clusters is more than just a beautiful halo. It is a statistical treasure trove. By counting how many clusters exist at different masses, they can construct what is known as the globular cluster mass function. It's a cosmic census that should, in theory, follow a predictable and smooth pattern, with smaller clusters being far more numerous than the rare, massive ones. But when this census is taken for the clusters around our supergiant galaxy, the results reveal a curious anomaly, a strange and unexpected kink in the data that points to a history far more complex than a simple, peaceful aging of stellar systems. In an undisturbed environment, the distribution of globular cluster masses should follow a gentle, sloping curve. Imagine a graph where the vertical axis shows the number of clusters and the horizontal axis shows their mass. You would expect to see a very large number of low-mass clusters, with the count steadily dropping off as you look toward higher and higher masses. This pattern reflects the initial conditions of their formation billions of years ago, when giant molecular clouds fragmented to give birth to these stellar families. The curve should be smooth without any sudden dips or bumps. However, the data from NGC 4889 shows a clear deviation from this ideal. At a specific mass range, roughly around several 100,000 times the mass of our Sun, there is a noticeable deficit of clusters. It's as if someone reached into the population and selectively removed clusters of that particular size, creating a gap or a dip in the otherwise smooth distribution. This missing middle weight of clusters is the central mystery of the mass function. The most likely explanation for this strange dip involves a brutal process of gravitational selection, a cosmic editing that has been ongoing for billions of years. Globular clusters, for all their dense packing, are not indestructible. As they orbit the galaxy, they are subjected to two primary destructive forces. The first is tidal shocking. Every time a cluster passes through the dense galactic plane or makes a close approach to the massive galactic core, the difference in gravity's pull across its width gives it a gravitational jolt. This repeated shaking can strip away stars from the cluster's outer layers, gradually eroding it over time. The second force is dynamical friction. More massive clusters, due to their stronger gravity, interact more significantly with the background sea of stars in the galaxy's halo. This interaction saps their orbital energy, causing them to spiral inward toward the galactic center, where they are most vulnerable to being completely torn apart by the central supermassive black hole. This is where the mass-dependent nature of the destruction creates the observed dip. The very lowest mass clusters are so fragile that they were likely destroyed completely early in the galaxy's history, leaving no trace in the current population. The very highest mass clusters are so robust and tightly bound that they can withstand the tidal forces and survive to the present day. The clusters in the intermediate mass range, however, occupy a precarious zone. They are just massive enough to have survived the initial eras, but not so massive as to be immune to the slow, grinding destruction over billions of years. They are the ones currently being actively eroded. The dip in the mass function, therefore, is not a sign of how they formed, but a snapshot of how they are being destroyed. It marks the mass range where clusters are being efficiently dismantled by the galaxy's harsh gravitational environment. Yet, destruction is only one side of the story. Intriguingly, some observations suggest that the mass function might also show a slight excess of clusters at the very high mass end. This bumps the mystery to another level because it hints at a creative process that runs counter to the destructive trend. How could new, massive clusters form in a galaxy that is supposedly red and dead? The answer may lie, once again, in the galaxy's violent merger history. During the collision of two gas-rich galaxies, the immense pressures can trigger the formation of spectacularly massive and dense star clusters, known as superstar clusters. These objects are essentially young globular clusters. If NGC 4889 consumed a galaxy that was undergoing such a starburst, it would have acquired a fresh population of high-mass clusters, injecting them into its halo and subtly altering the high end of the mass function. The overall distribution we see today is therefore a palimpsest, a layered record written by both the relentless forces of destruction and the occasional, violent acts of creation that have shaped this galactic giant throughout its long existence. But beyond the grand structures of radio lobes and magnetic fields, the influence of this supergiant galaxy extends to the realm of the truly minute and unimaginably energetic. We now turn to a strange object that is not an object at all in the traditional sense, but a relentless rain of atomic shrapnel pelting our own planet, high-energy cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, that have been accelerated to velocities infinitesimally close to the speed of light, carrying energies that dwarf anything produced in human particle accelerators. While cosmic rays come from many sources, there are tantalizing indications that NGC 4889 acts as a formidable natural particle accelerator, and the faint trails of these particles detected here on Earth provide a unique window into the most cataclysmic events in the galaxy's past. The journey of a cosmic ray from a distant galaxy to Earth is a story of immense power and random chance. The particles themselves are born from relatively ordinary matter, likely stripped from the hot plasma within the galaxy or from the atmospheres of stars. What transforms them into high-energy bullets is a process of gradual acceleration, a cosmic slingshot effect that can occur in two primary environments associated with NGC 4889. The first is within the powerful shock waves that once expanded at the leading edges of its AGN jets. As these jets slammed into the intergalactic medium, they created colossal shock fronts, regions where the plasma's density and magnetic fields changed dramatically. A proton or atomic nucleus caught in these shocks can bounce back and forth across the shock boundary, gaining a little bit of energy with each crossing, much like a ball being volleyed between two rapidly approaching rackets. Over time, this Fermi acceleration can boost a single particle to energies exceeding 1 trillion electron volts. The second potent accelerator is linked to the galaxy's violent merger history. The collision of two galaxies doesn't just rearrange stars, it sends immense pressure waves rippling through the intracluster gas. These merger-induced shock waves can be just as effective as jet-driven shocks at energizing particles. In the turbulent aftermath of a major collision, magnetic fields become tangled and amplified, creating a complex web of magnetic mirrors that can trap particles and force them to gain energy as they are compressed and shaken by the passing shock. The sheer scale of these events means the acceleration region is enormous, allowing particles to reach the highest energies conceivable. Once these particles escape the confines of the galaxy and its immediate environment, they become cosmic rays, traveling in near straight lines across the intergalactic void, their paths only slightly bent by the weak magnetic fields that permeate the cosmos. Detecting the specific origin of any single cosmic ray is one of the greatest challenges in astrophysics. Because most cosmic rays are charged particles, their paths are deflected by magnetic fields throughout their journey, making it impossible to trace them back to a specific point in the sky like we can with photons of light. Instead, scientists must use statistical methods. When the highest energy cosmic rays, those with energies above a certain threshold, are mapped across the sky, their arrival directions are not completely random. They show a slight correlation with the positions of nearby active galaxies and large-scale structures. Given its immense power and past activity, NGC 4889 is a prime candidate for being a significant contributor to this diffuse background of high-energy particles. It's a forensic approach where we cannot name a single culprit, but we can identify a powerful suspect based on motive and capability. To overcome the directional challenge, astronomers use an ingenious indirect method. When an ultra-high-energy cosmic ray, often a single proton with the kinetic energy of a professionally thrown baseball, strikes the upper atmosphere of Earth, it creates a spectacular cascade of secondary particles, a sprawling shower that can be detected by specialized observatories covering dozens of square kilometers. By studying the profile of these extensive air showers, the number and type of particles that reach the ground, scientists can work backwards to estimate the original cosmic ray's energy and, crucially, its mass or nuclear composition. This is a vital clue. If the highest energy events are dominated by light nuclei like protons or helium, it suggests they were accelerated in environments with strong, relatively clean shock waves like those from AGN jets. If heavier nuclei like iron are found at these extreme energies, it might point to acceleration in the more complex, chemically enriched environments found in starburst regions or the turbulent interiors of merging galaxies. The existence of a source like NGC 4889 helps solve a long-standing mystery in physics: how particles can be accelerated beyond a theoretical limit known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. This limit predicts that the highest energy cosmic rays should interact with the cosmic microwave background radiation, the leftover glow from the Big Bang, and lose energy over long distances. Our source is billions of light-years away. This should make it impossible for us to detect them. The fact that we do see these particles implies that they must come from relatively nearby sources within our local supercluster of galaxies, or that the acceleration mechanism is so extraordinarily efficient that it can overcome these energy losses. The powerful, recurring shocks generated by the past mergers and AGN outbursts of a nearby giant like NGC 4889 provide exactly such an efficient engine, capable of launching particles on their incredible journeys across intergalactic space. The detection of these cosmic rays is therefore more than just a record of past violence. It is a direct probe of the ultimate limits of particle acceleration in the universe, a natural experiment conducted on a galactic scale. But perhaps the greatest source of strangeness is not an object within the galaxy at all, but the very nature of our observation. When we point our most powerful telescopes at NGC 4889, we are not seeing it as it exists today. We are looking directly into the deep past. The galaxy is so incredibly distant that its light takes over 300 million years to travel across the cosmic void to reach our eyes. This means the image we capture is a snapshot of the galaxy as it was during the Carboniferous period on Earth, a time when vast swamps covered the planet and the first reptiles were beginning to appear. This cosmological time delay, a consequence of the finite speed of light, transforms the galaxy from a contemporary object into a living fossil, allowing us to study a crucial chapter of cosmic history that has long since concluded. This time dilation effect offers a phenomenal advantage. NGC 4889, in its current observed state, is a mature quiescent giant. By examining it, we are essentially performing an autopsy on a galaxy that has already completed its most dramatic phases of growth and activity. We can study the end products of billions of years of galactic evolution, the stable supermassive black hole, the ancient stellar populations, the completed merger remnants, with a clarity that would be impossible if we were watching these events unfold in real time. It's like having the complete, finished manuscript of a novel instead of trying to understand the story by watching the author write it one word at a time. This fossilized perspective allows us to test our theories of galaxy formation against a known outcome, providing a critical benchmark for understanding how the universe's largest structures assemble themselves. However, this same time delay presents a profound challenge when it comes to observing anything transient or short-lived. Imagine trying to understand the life cycle of a mayfly by only being allowed to look at it once every year. You would see a static, lifeless form and miss its entire brief, vibrant existence. Similarly, any event in NGC 4889 that unfolds on a human timescale or even over a few million years is effectively invisible to us. The brilliant outburst of a supernova, the flaring of an X-ray binary, or the final merger of a binary black hole system, if such an event occurred in the galaxy, the light announcing it would not arrive for another 300 million years. Conversely, if we were to see such an event tomorrow through our telescopes, it would have actually happened when dinosaurs were the dominant life on our planet. We are forever studying a galaxy's history, never its present. This creates a fundamental limitation on our ability to witness dynamic processes. The erratic X-ray binary we discussed earlier with its unpredictable outbursts is a perfect example. From our fossilized perspective, we see its tantrums as they happened in the deep past, but we have no way of knowing what it is doing now. It could have fallen permanently silent, or it could have entered a period of hyperactivity that we will not witness for eons. This temporal disconnect means we can never have a real-time conversation with this galaxy. We can only read its diary, an autobiography written in light, where each entry is separated by millions of years. Our understanding is therefore based on statistical probabilities and long-term averages, piecing together the galaxy's life story from fragmented clues left behind in the slow-motion film reel of cosmic history. As we reach the final strange object in our catalogue, we must shift our perspective from what this galaxy is to what it will become. Our journey has taken us through the relics of its violent past, but the story of NGC 4889 is far from over. It sits today as the undisputed heavyweight champion of the Coma Cluster, a title it has earned through eons of cosmic conquest. Yet the universe is a place of constant change, and even this Leviathan's destiny is written in the relentless laws of physics, playing out on timescales that dwarf human comprehension. The ultimate strange object associated with this galaxy is not something we can see, but the future that awaits it, a future of unimaginable solitude and gradual dissolution. In the immediate cosmic sense, over the next several billion years, the most predictable chapter in NGC 4889's future is one of continued galactic cannibalism. Its immense gravitational pull ensures that it resides at the very bottom of the cluster's potential well, making it the ultimate sink for any smaller galaxy unfortunate enough to wander too close. We can expect the ghostly stellar streams surrounding it to multiply and intertwine. The delicate ultra-diffuse galaxies orbiting it will, one by one, be stretched into new streams, their stars adding to the growing halo. A major merger with the cluster's other giant elliptical, NGC 4874, is even a possibility, which would create a single, truly monstrous galaxy that would dominate the cluster entirely. This era of growth via consumption, however, has a finite endpoint. The universe is expanding, and on the scale of galaxy clusters, this expansion manifests as a gradual evaporation of the cluster itself. Over hundreds of billions of years, the gravitational bonds holding the Coma Cluster together will weaken as the space between galaxies stretches. The smaller satellite galaxies will be the first to be lost, drifting away into the expanding void one by one, until NGC 4889 is left with fewer and fewer neighbors to consume. It will become a king whose subjects are slowly vanishing, its empire dissolving around it. The fate of its most famous resident, the 21 billion solar mass supermassive black hole, is a story of profound patience and eventual silence. For trillions of years, it will likely remain dormant, a sleeping giant in a darkening galaxy. But eventually, even a quiet black hole can find a meal. Through a process known as dynamical friction, the random motions of the stars in the galaxy's core will slowly cause them to sink toward the center. Some will be slung away as hypervelocity stars, but a fraction will be sent on trajectories that bring them within the black hole's event horizon. This will provide a trickle of accretion, perhaps causing the black hole to flicker with faint, sporadic activity. A more dramatic feast could occur if a stellar remnant, a white dwarf, neutron star, or even a stellar mass black hole, is drawn into a close orbit. The tidal disruption of such a dense object would release a brilliant flash of energy, a final shout in the growing cosmic silence. But these events will become exponentially rarer as the galaxy's stellar population ages and stars drift further apart. On the longest scales, governed by the speculative physics of quantum mechanics, the black hole's end is one of slow evaporation. Stephen Hawking theorized that black holes are not entirely black. Due to quantum effects near the event horizon, they should emit a faint glow of radiation, now called Hawking radiation. For a supermassive black hole, this process is incredibly slow. It would take an almost inconceivable amount of time, far longer than the current age of the universe, for a black hole of this mass to lose a significant fraction of its energy. But in a future where all stars have died and the universe has expanded into a cold, dark expanse, this Hawking radiation would be the black hole's only legacy. As it radiates, it very slowly loses mass, and this process accelerates as the black hole shrinks. The final moments of NGC 4889's black hole, trillions upon trillions of years from now, would be a sudden, explosive burst of particles as the remaining mass converts entirely to energy. It would be a final, ephemeral spark, the last testament to a galaxy that once ruled a cluster. This contemplative journey forces us to see NGC 4889 not as a permanent structure, but as a magnificent temporary edifice in the cosmic flow. It represents a phase in the life cycle of matter in the universe, a phase of maximum organization and structure. It formed during an era when gravity could efficiently pull matter together into dazzlingly complex systems. But the expansion of the universe, driven by the mysterious force of dark energy, appears to be accelerating. This suggests a future where the collaborative power of gravity is ultimately overwhelmed. The giant elliptical galaxies of today, the NGC 4889s of the cosmos, may be the last great monuments that the universe will build. They are the pinnacle of galactic evolution, the final products of an era of collisions and mergers. After them, the long winter sets in. Stars will age and fade, galaxies will drift apart, and the universe will become a colder, darker, and increasingly lonely place. In studying this one supergiant galaxy, we are therefore reading a chapter from the ultimate biography of the cosmos, a story that stretches from a fiery beginning to a silent, distant end. Its 50 strange objects are not just curiosities, they are the clues that allow us to trace this grand narrative, a narrative in which even the mightiest giants have their time, and then gracefully fade into the history of deep space. And so, our journey through the strange and wondrous contents of NGC 4889 draws to a close. We have ventured from the silent, sleeping titan at its heart to the faintest whispers of light between galaxies, uncovering a collection of cosmic oddities that challenge our understanding of the universe. From the hypervelocity stars flung into the eternal dark to the potential dark galaxies that are nothing but pure gravity, each object tells a part of a larger story. This is not merely a catalogue of 50 peculiar things. It is a single, integrated narrative about the life, death, and enduring mysteries of a supergiant galaxy. What becomes overwhelmingly clear is that this one celestial object serves as a perfect microcosm for modern astrophysics. Within its vast domain, we find active laboratories for studying the nature of dark matter through gravitational lensing and distorted stellar streams. We see the dramatic life cycles of stars, from the rebellious blue stragglers cheating death to the lonely planetary nebulae glowing in the void. Its history is written in the chemical gradients of its stars and the concentric shells that ripple through its halo, a direct record of the violent mergers that built it. The galaxy presents us with extreme physics, from the overmassive black hole that defies scaling relations to the ultraluminous X-ray sources that push the limits of accretion. Every major question about the formation of structure, the role of supermassive black holes, the interaction between galaxies and their environment, and the very nature of dark matter finds a piece of its answer within the confines of NGC 4889. This exploration underscores a profound truth about our place in the cosmos. We are not separate observers looking at a static universe. We are embedded within it, using the finite speed of light as a time machine to read the autobiography of a giant. The light we see today left that galaxy when great forests first grew on Earth, making every observation an act of cosmic archaeology. The mysteries we are unraveling are not abstract. They are fundamental to understanding where we came from and what the future holds for all the structures we see in the night sky. The story of NGC 4889 is a powerful reminder that the universe is a place of constant, dynamic change, operating on scales of time and space that both humble and inspire. It encourages us to keep looking up, to keep questioning, and to remain awestruck by the sheer ingenuity of nature. If you found this deep dive into the cosmos as fascinating as we did, and you want to join us as we unravel other space mysteries, from the enigmas of black holes to the secrets of the early universe, please consider subscribing to the channel. Hit the notification bell so you don't miss our next journey into the unknown. The universe is full of stories waiting to be told, and we're just getting started. Thank you for watching.